I solved four
Is recording or not? Camera. तो ऑनलाइन YouTube it is not shown. इस साइड
हो रहा सर मैंने लाइट चालू कर दिया सर सर अभी स्क्रीन अभी शेयर करूं
1 मिनट बच्चे को आने दो
हाँ
1 मिनट बच्चे
four times for case solved quickly. Next attempt. 10 times. 10 times. Only in beginning. And change two values.
10 by 10 matrix. Only big any matrix.
Only small sizes. So
One side is always
Mathematica works perfect.
bigger size is
For Mathematica, no problem because works exact computation. And exact computation don't know what is your condition or better condition.
उधर भी मूव होने से आई वीडियो आई
हाँ
उधर भी लिखी थी
हाँ उधर हाँ
कहीं पे भी इसके अंदर में कहीं पे भी लिखा है ओके आई गेट मूव है डाउन ना
वीडियो आ गया रिकॉर्डिंग में तो पूरा आएगा सर हमने रिकॉर्डिंग में इवन बोर्ड तक कैप्चर किया है
ओके Now we are going to start the first session of third day, okay, of this program. So In morning session, I will be talking, and after that, the Professor Dekra will be giving his talk. Okay. So today we'll discuss about the, start it. Yeah, pointer, pointer, pointer. Pointer. Fine. What is it? Pointer is a pointer. Yeah. Once you make ready, then. Yes. Abhi sir, start fusing. Okay. Good morning to everyone. So today I'll be talking about the least square problem and the QR decomposition. This is our third day, and this is the first session. So in this, we'll discuss about the least square problem and the QR decomposition. So first of all, I'll discuss about the QR decomposition and its stability analysis. Also, whether this method is stable or not. Okay, that all we'll discuss. So in this, I will be covering this description of least square problem and for the rotators and the reflectors and the QR decomposition, because these rotators and reflectors are the key operators which will be used to find the QR. Q is orthogonal matrix and R is upper triangular matrix. Okay, and the solving least square problem by the QR decomposition, and then we'll discuss a little bit gram schemic orthonormalizations, and which will give you QR decomposition. Okay. Also theoretical some foundation, and we'll give and updating the QR decomposition when rows or columns are added or deleted. Okay. So what is the least square problem? So first you give the highlights that many real world problems involve inconsistent systems of equations. Okay, we seek an approximate solution that minimizes the error, and this leads to the minimum of x minus b. This is norm 2. Okay, instead of norm 2, you can take the Frobenius norm or 1 norm or infinity norm. It depends on your problem. Okay, and this is best one is this 2 norm. Because the computing the 2 norm, matrix 2 norm, is difficult, That's why people avoid this and they used to take Frobenius norm. Frobenius norm you are just taking. But here you just see this is also Euclidean norm of two norm. Euclidean norm, or you have this is Frobenius norm also. Yeah, in vectors. Okay. And you can have the infinitely such s, and you are finding the one which gives you minimum norm. Okay, that's the idea of this. In our previous lectures, we have seen that the A is a non-singular and have the LE decomposition. Here in the QR decomposition where we discussed, it can be for the non-square matrix. If it is a non-square matrix, we can use to solve the least square problem. Okay. Application is a data fitting, signal processing, machine learning, and the control system. Everywhere people are using optimization theory, but they name different way. So machine learning people, they use to tell machine learning because they do optimization. And you have the many constraint equations, and they used to solve by using the Lagrange or the KKT form. And the problem is convex, as I told you in the beginning of my lecture. Okay, machine learning and the control systems, and also the vibration people are using. So here just a highlight, if you have a data set, okay, and you want to make the polynomial approximation, say for example, linear polynomial, then you have this PT equal to A0 plus A1T, okay. And what you have suppose n data, you just are feeding with this Ri equal to Yi minus Pti, because this is the residual. Okay, Ri equal to Yi minus Pti. Because if the polynomial equation, if you have, the always you have error, and that error is Ri, this for the I star. Okay, and consider this Ri is as a vector R1 up to Rn. Okay, so basically what we are doing that we seek Pt that minimizes the residual norm. You will find the linear polynomial which would give you this visibility. And for such data, you just fit this polynomial PT. And different norms will lead to different problems. Say, as I told you, you just take the one norm of this R because it is just a sum of this Ri. Okay. And if you take the infinity, you just take the maximum of Ri. Okay. I varies from 1 to n. And for the two norm, as here in case of the vector, it is two norm and the Frobenius norm are same. Okay. This you are taking this. The most widely used and best understood is the least squares approach. This is minimum of A0, A1 and norm 2 square equal to this. So what you are doing basically, this is you just find the critical points and you are checking whether this minimum or maximum, and then by using the calculus methodology you are doing. Is not it? Yes. But here we are not going to use the calculus. You just by numerical linear algebra technique you can solve that one, and that you can use the QR decomposition to solve this kind of problems. We are not going to calculus to solve this problem. Okay, it has multi-variable calculus. You have to give these critical points, and once you will find the critical points, then you check for the maximum and the minimum. Okay. If measurement errors, there are errors in YR, this is independent, normally distributed, and mean zero constant variance this, then minimizing this gives you the maximum likelihood estimator and justify use the two norm in the least square problems. So here you have called the discrete least square problem. The kind of problem if you have in data set and if you are finding this solution, this is called discrete least square problem. Okay, because you have discrete points, and if you have continuous points, then you have to take the integration. Okay, so you can find the this one. Now similarly, suppose if you want to make your data fit into the nonlinear, say polynomial. Okay, so n degree polynomial. So in that case, say if it is a polynomial, then it has a basis, and these are the monomials 1 t minus 1. So any polynomial of degree m can be written as the linear combination of this power, where x1, x2, and xm are the coefficients that you have. That any basis vector, if you have any polynomial in the vector space, you can write the linear combination of these monomials. So alternate basis may improve the numerical stability. You may have other bases also, but here we are taking this basis. These are the standard basis for the polynomials. Okay. So what you do is that for n data points and m basis function ax, this is equivalent to b, because due to machine error, truncation error, you won't get the exact ax equal to b, and you'll be getting approximately ax equal to b. Okay, where a is a n by m matrix, and this aij, this phi j ti, these are the entries of these matrices. So if you put all the data, say ti, I went from 1 to n, and you will be getting a matrix equation that x equal to b. Okay, because here you see the if I put this pti and then x1 ti, phi 2 ti, and xm mti, this is equal to yi. So if you write I went from 1 to n, then y1, y2, yn, it is a y vector, and you will be getting also b vector. Then also you can get a matrix A. The x is the Rm coefficient vector, and b is this is vectors of yi value. If n is greater than m, this is called overdetermined system. Okay. So basically, whatever we got in the previous slide, if you want to make your data point it's approximate to the polynomial equation, first you have seen the linear, and similarly one can do for quadratic and biquadratic, and one can go through for general polynomial gap. Okay. So finally, you would be getting a matrix equation x equal to b. So whole idea is to solve this matrix A, and you will get the coefficient. These are the coefficients in this A and G matrix you will be getting. Okay. Now we seek x, minimizing the residual r equal to b minus ax. That means we need x for which this minimum x b minus ax norm 2 square, includes the fitting with the polynomials, and also you can try for a trigonometric functions exponential any basis positive. So here basis we have taken the standard. If it is a polynomial, it may be the transcendental equations you may have. You may have the irrational equations after we have. So likewise, this the first I have taken these polynomials where the monomials are 1, 3, t square up to t to the power minus 1, and you are okay. So instead of that, you can have the trigonometric functions also, because some of the polynomials can be written, transcendental equations can be written in terms of the trigonometric functions. Okay, and also you can write in the form of exponential and any basis function also positive. So okay, now we'll solve the least square problem using this normal equation ATA equal to ATB. Okay, that ATA user and the orthogonal transformation, that is a QR decomposition you can make, and then we can solve this. This technique ensures numerical stability and the efficient computation. This will show later on how this QR decomposition will be used to solve the normal equation ATA and any least square problem. Okay. Now, so before going to compute the QR decomposition, we have to know the rotators. That is, sometimes it is called GIAN rotations, because the scientist GIAN has given this technique. So it is named GIAN rotation is named, it is again. So now you have this shape. For example, theta is a linear transformation, q equal to cos theta minus sin theta cos theta, x, and any vector x by rotating its counterclockwise. This matrix is called rotators. This is an operator which rotates through an angle theta. Okay, so this is the rotators, and this is the orthogonal matrix. Okay. Now you can see this, if that previous one is the Q matrix, orthogonal matrix, then QTQ equal to identity. As you know, Q is orthogonal and determinant of Q equal to 1. And its beauty is that inverse equal to its transverse, because QQT equal to identity. So no need to find the inverse, you just make the transpose of that matrix, you will get the inverse. Inverse of a rotator is a rotation through a minus theta. And rotators preserve, this is isometry, this is phi x norm equal to norm of x. So as I previous class I told you, and orthogonal transformation and this unitary transformations are invariant under norm. This is the invariant, okay, with respect to the norm, to norm, or the Frobenius limit. Okay. Now, how will you find these rotators? Suppose you have a vector x1, x2, and say x1 not equal to 0, and you can find the q such that qtx equal to y0. For that, you can choose cos theta equal to this is x1 square plus x2 square, and sin theta x2 x1 square plus x2 square, and this ensures the sin square theta plus cos theta equal to 1. Basically, you will find this q for which this first entry is non-zero and the second entry is zero. Okay, so this is the whole idea, because if we have this q is cos theta and sin theta, and then just you operate with the x, you will get this equation that is x1 square and x2 square. So for example, if you have cos theta sin theta minus cos theta minus sin theta cos theta, and you just put this x1 x2, this is first entry would be 1 0, and this would be b. If you solve this, okay, if you solve this, because this is cos theta, this is minus sin theta, this is minus sin theta, and this is plus. If you do, if you work to this, if you go to this one, you will solve this x1 cos theta plus x2 sin theta, and this is minus x1 sin theta and plus x2 cos theta. This is equal to star 0. So then we just take this minus x1 sin theta plus x2 cos theta. For choice is first one, you can okay. This is star and this is 0. This is x1 and x2, and you can just think what would be the cos theta and sin theta, because you can take x sin theta equal to x2 and cos theta equal to x1. This is also, but this choice is not appropriate because sin square theta plus cos square theta equal to 1. So the option is sin theta, you can choose this x2 divided by x1 square plus x2 square, and this cos theta, you can choose this is x1 divided by x1 square plus x2 square. Okay. So basically, we are finding q for which this first one is non-zero and this would be 0. If you make it equate this equal to, you will get x1 square plus x2 square, because this is equal to this one. Okay. So basically, we need the q for every x, there exists a rotation matrix q for which this is 1, and this norm is non-zero quantity. Any non-zero quantity you can take. Here we have taken norm of x. And the rotation vector x into x-axis, this is a basic step in constructing the QR decomposition. This is the basic steps to construct the QR decompositions. So here, if A is a matrix with this applying rotators, we can form Q transpose A equal to R, where R is a upper triangular matrix, and this generalizes a square matrix. For such, there exists orthogonal Q and an upper triangular matrix R such that QT A equal to R. So this is the foundation of QR decomposition. Now you see later on, for any matrix, that means you have this A equal to QR, Q2 A equal to R, you just multiply both sides of Q, you will get A equal to Q to R. This is the upper triangular matrix. R will be upper triangular matrix. And this is the fundamental in solving the least square and the linear system that we'll see later on. Okay. Now, say for example, if you have this Ax equal to B, rewrite as just you multiply instead of A, you just take this QR x equal to B, and you do substitute y equal to Rx and the Qy equal to B, and then you will get the y equal to QTB. So we have seen in our previous lectures in the LED decomposition, R is the upper triangular matrix, and you do backward substitution, you will get the solution. Okay. So advantage is QR decomposition is especially useful when A is a full length but not square or poorly conditioned for LU. It is not as similar to LU. LU sometimes gives a numerically instability, but QR decomposition will give you stability. Okay, and it takes more flops than LU, but it is a more stable one. Okay. Now you have this A equal to QR. In the both the cases, you have this and Rx equal to C, and then you put C equal to Q to B and Rx equal to C. This is some methods from two equivalent perspectives. Here is one example. Suppose X equal to B, A is this 1, 1, 0, and B equal to T0, and construct this. Say, for example, X equal to 1, 1. This is the first column of this matrix 1, 1. So I have taken as the X, okay? And then what I did, you just put this is X1 and this is X2, and apply the formula that is X2 by cos theta equal to here X1 by X1 square plus X2 square, and this is X2 by X1 square plus X2 square. And this would give you, and then you got this is cos theta, this is sin theta, this is cos theta minus sin theta cos theta. So just you put this and you will get the Q matrix, and this is the orthogonal matrix. And if you do multiply with the this, you got this R QTA, you will get R matrix, because QTA, if you just put you will get the upper triangular matrix, but here you are getting diagonal matrix. I think this is 0, and C equal to QTB, you will got this one. So solution, finally you will get the solution X equal to 1 minus 1. Okay. Now, the previous slide tells you about the 2 by 2 matrix, and if we can generalize it to n by n matrix. Okay, it is, say for example, a plane rotator is an n by n matrix that looks like the identity, except 2 by 2 block in rows and the columns are in this. Yes, it looks like the identity matrix, and the last entry is also 1. And here cos theta minus sin theta cos theta, this say ijth entry you want to make this equal to 0, you have to apply your given rotation to make this happen. So what exactly you are doing here is that, suppose your matrix is there, say in the matrix you have like this, say this is n by n matrix. These are the entries. This is say n by n. What I do is that, so I apply this rotators to make this matrix to upper triangular matrix. So for this entry, if you want to make this, you have to make one rotator, so that this entry will be equal to 0. So likewise, you need n minus 1 rotators. How many? N minus 1 rotators to make first column, okay? The first column to be equal to 0, except the first entry, okay? Except first entry, yeah. So how many rotators you need? Say for example, here the Q21 transfers, and this is Q2, Q31, and this is you need Qn1. This transfer, and if you make it into matrix A, and this your matrix will look like, except the first entry, all would be equal to 0, but this would be again the entry, some entries would be there by multiplying whatever you have, this is n by n. Clear? So if you want to make this equal to 0, this is minus 2, 1 plane. So ij, let's say I equal to 2 and j equal to 1, say. So from there you have a formula, you just put this, and that two entry you just take from this to this entry, you take I and J, okay, and that the substitute, you will get this rotator matrix Q21, and similarly for the A3, A31, to make this equal to 0, that means X3 and X1, okay, and you just take this given rotation, and then you do multiply again and again, you will get the first step. Similarly, you have to make, you don't want to touch this entry, you want to make this one. That means this is the position, how much? This is the third row, Q3, again you need Q3 to transport, and this is Q3, 3, okay. This is the which okay. This one you have this one. So what is the position of this? This is Q 3 2 second column. Okay, and then you are going for, because we don't want to make this equal to 0, because okay, this is the Q2. Okay, there Q3 2 and Q3 3 and Q3 4 and this Q3, sorry, this is 4 3, okay, this is Q3, this is Q4 2 and Q4 3, and this is Q N, okay, 3 4 5, and this is N2 5. Okay, so this is Q3 2 4 5 3, and this is N3. This is 2. Okay. So likewise, in every column you need this kind of rotator. Okay. So you will get this given. Because that means you need like this Qn minus 1 transpose, this again, and so on. You will get this matrix A, you will get the R matrix. Okay. Yes, sir. The last entry you are making this, and this is of Qn minus 1, okay, because the last column you don't want to touch, because non-upper triangularity will be lost. So likewise, you would be getting a n minus of, in the first case you need how many rotation? N minus 1 rotation. Okay. In the second you need n minus 2. In the third you need n minus 3. And in the last one, you will get the 0 rotation, because last column you don't want to touch after giving n minus 1. You. But the beauty of this, that the product of orthogonal matrix is orthogonal matrix, and all this product would be this transpose and A equal to R, and this product of orthogonal matrix would be Q, and this is P, A equal to R. And finally you will get this, and A equal to QT inverse, this is R, and this means A equal to Q. So likewise, you can get the upper triangular matrix by using your given solution. Okay, so Q is orthogonal, and this determinant of Q equal to 1. So this is one idea, is that if ijth entry you want to make this, you just take xi and yj, and from x equal to this one, and then you form the cos, so C for cos, sine, this xi by this, and xj by this one. Then form, if xi and xj both are equal to 0, in that case you just substitute cos theta equal to 1 and the sine theta equal to 0. Only the ith and jth entries are modified. A plane rotator acts on vectors in Rn by rotating only in the I, xi, and xj plane. Okay. A vector x can be uniquely decomposed into this one, because the plane rotators, you can use this concept for getting rotators. Okay. Here you can see only components of x along axis I and j are affected. So when you take the given rotation and you want to make ijth entry to be equal to 0, in that case, the other entries would be remain unchanged because all the entries are 1, 1, 1 in the diagonal and the off diagonal entries are 0 except J term. Okay, cos, sin, cos. Okay. Okay. So as I discuss here, and these are the concepts that apply rotators Q21, Q31 to 0 out except 1, 1 column. And these rotators only affect rows below the current pivot and preserves existing zeros above. And proceed to column, again you will be getting the n minus, how many? N minus, first you got n minus 1 rotators, okay, except this below 2, the entries A to 2, rest of the entries will be 0. And likewise repeat the process for column 3 through n minus 1. Okay, and then you will get this one q equal to this and r equal to q2. So all this q n minus 1 up to q2 minus 1. Since q is the product of orthogonal matrix, q itself is orthogonal. So product of orthogonal. And the cost of QR decomposition via rotators, you can show that this takes order of n cube clause. So we'll show how to calculate this one, because for each k 1 to n minus 1, we apply the given rotation to eliminate entries below the diagonal. Okay, so number of given rotation per column is n minus k. Is not it? It is n minus k. For k equal to 1, you got this n minus 1, n minus 2, and so on. You got this. Each given rotation affects only 2 rows. Only 2 rows it affects. It requires 2 into n minus k clause. Only 2 rows it affects. Okay, not all. So in this case, k varies from 1 to n minus 1, and you have this because addition and multiplication is there 2 into n minus k. If you add and subtract, and you have similar n minus k columns are there, and k varies from 1 to n minus 1. So if you add totally, you will get around 4 n cube by 3 plus, and if n is very large, if you do multiply here, you will get the 4 n cube by 3 plus, and you will get all of n cube plus. Okay. So similarly, we can discuss about the reflectors. This is one technique, the rotators, where we are using to get the QR decomposition. Similarly, we have the reflectors. So reflectors are the faster than the rotators. Okay, if you get the reflector, and instead of making entry y 0, you will make all at the time equal to x. You will get directly 0, 1 reflector is enough to make all the columns 0 except the first entry. So this is more faster than the rotators. So here you just see the construct the Q that reflects any vector x across a line L through the origin. Okay, and suppose how to construct these reflectors. Okay, the way we have constructed given rotator, similarly we can construct reflectors. Here is suppose V is a non-zero vector on the line L, okay, and U be the unit vector orthogonal to L. If they are orthogonal, then any x, because these are the x can be written as a linear combination of these. These are the basis vectors, and any vector in say R2, say for example, if we have two bases U1 and U2, you can write alpha U1 plus beta U2 like this if they are perpendicular U and V. And any vector in the line in R2 can be written as this one, linear combination. And the reflection, its reflection would be like this, x equal to minus alpha u plus beta v. Just to the mirror, you just put on the line here, and if the vector is there, it will come like this. And opposite, this should be reflection of that. And now if you do substitute, say p equal to, you are taking u ut, and the u ut you just take where u is a unit vector, that means norm is equal to 1. Okay, and define this q equal to I minus 2p. Okay, if you write this one, then this q would act as a reflector, because q of x I minus 2 u ut, x is the reflection of x through the hyperplane orthogonal to u. And this is the this is your reflector, and this q is a symmetric, q equal to qt, and also it is orthogonal, and determinant of q equal to plus or minus. Okay, So now here you see, if you have this u and this you can write instead of 2, you can also write in the form of u norm 2 square uut, because if u is not orthonormal, in that case you can divide also. This is 2 by gamma. If it is orthonormal, that this is 1, and so 2 uut also. So it is exactly same. If you take a u divided by u norm 2 and u divided by another u norm 2, you can give another name v transpose. So it is the same as the I minus 2 u transpose. And this q is a reflector with the following properties, and the q u equal to minus u and q v equal to v for all v, such that which is perpendicular to v. Okay. And the proof is simple. You just take any vector u, which is the unit vector is equal to 1, and you just define q equal to I minus 2 u ut, and you just operate with the u, you will get minus. And if you will operate with the v, you will get, okay, because u and v are orthogonal. Say this is v minus utv equal to 0, and this is equal to v. Okay, and similarly here is the u minus, because utu is the unit vector, so u minus 2u, this is u, and utv. The q reflects vector through the hyperplane through the orthogonal to u. Okay, now here is this beautiful theorem that any x, y in Rn, okay, and where x not equal to y, but their norms are same, then there exists a unique q, and this is reflected qx equal to y. Okay, so this is the existence of the q, where qx you operate and you will get this y, where xy is in Rn. Okay, any vector in Rn if it is given, and they are not same, but their norms are same. Okay, then you can get this. This is standard way. So if you have x and y, you can construct u equal to x minus y. Then you just define q equal to I minus 2 u norm 2 square uut. So from here, you can find that you can decompose the x in this form, because this is half x, this is half x, this is half y, half y. It will get cancelled, you will get x. And here you say, not x minus y equal to u, already we have substituted this one, and x plus y is orthogonal to u. Okay, not it. And if you do product, you will get this here, but these are orthogonal. Similarly, you have q of x minus y, this is equal to minus y, this is y minus x, and this is v is a qv, you can get qx and q equal to x plus y, and you can just form this one, because x you can write like this, and that x plus y divided by, because q of x equal to, from your previous equation, you have q of x equal to what? This one. Q of x minus y equal to y minus x. So from here you can find this one. This is qx equal to y. So this is the q you can construct if two vectors are given in okay, x and y are given, then you can construct u and you can construct v. Now here you can see, if you multiply with the any vector, if you that q, you construct a q and multiply with the any vector, it would give you 0, except the first entry. As I told you, if you multiply in the matrix, except the first entry, all the entries will be 0. Okay. Suppose your matrix A is there, you just take the first column and x. Okay. And that if you operate with this matrix here, the first column, and you will get except the first entry, all will be equal to 0. Similarly, if you apply in the second column, and you construct a q similarly as you did for the first case, and then accept the first two entries, and the rest entry will be. And similarly, if you go up to the nth case, then only you will get n minus 1 reflectors to get upper triangular matrix. You know. So first you need this first column q1 transpose A. You will be getting immediately q star 0 0, and the rest would be as it is, non-zero as this one. And similarly q2 transpose and the q1 pk transpose, and so on. You go up to qn minus 1 transpose. This will give you the operator. Yes. So this implies the Q1 and Q2 and this is Qn minus 1 and this is transpose and this is equal to R and this you just put this Q transpose equal to R and this implies equal to Q transpose inverse R, this is equal to Q. Okay. Got my point? So in reflectors, you can immediately construct that n minus 1 reflectors, you will get the upper triangular matrix. This is the statement reflecting mapping. And now here is the proof is just you take y equal to minus r 0 0 transpose, r equal to this one plus or minus x2, just you put this and you see that if this is y and you can see x not equal to y because r equal to this plus or minus x. They are x not equal to y, but their norms are same. You see norm of y equal to norm of x2, this are same. So if they are same, we can apply the previous theorem, there exists Q such that Px equal to 1. And here is the apply, there exists a reflector Q such that Qx equal to y. And any non-zero vector can be reflected to a scalar multiple of the first standard basis vector. This is useful in QR factorization via Hausdorff transformation. And this transformation sometimes it is called Hausdorff transformation or reflectors. So rotators, sometimes it is called Gibbons rotator. Okay. Okay. So here I'm going to show some stability of this method. Okay. Say for example, if you want to compute this norm of two norm of this vector on a computer that underflow in 10 to the power minus 10, assume each component of xi is smaller than 10 to the power minus 10. All are set to 0 if it is underflow. So if you put into the computer and you cannot find this norm of x2 because each component is about 10 to the power minus 10. So it is underflow at 10 to the minus. If you take the norm of this, so obviously you will get 0. Okay. So how to rectify this so that you won't get 0? So you have to do the proper scaling. How you will do this? You just take the beta equal to maximum of xi. Okay, because each of the component of x will be smaller than 10 to the power minus 10. So what you do? You take the maximum of this and just you if beta equal to 0 and then you set this is equal to 0. Okay, and if not, you just scale it. You just divide with the beta. That means z divided by norm of this one. Okay, and then you can then compute this z norm 2 equal to beta x norm equal to. So instead of finding norm x2, you just find the beta. But exactly you are doing same thing, but you do the proper scaling so that you won't go underflows or similarly for the overflows. So you have to do proper scaling. Sometimes if you have such kind of computation, and you have to be very careful if it is going underflow or overflow. So you do proper scaling. This is the one I am making the scaling. If the maximum coefficient, you just take the absolute value as a beta and you just divide beta each component. Then again you calculate the norm. So you save your data instead of going to 0. So here you see why it works. Now each of the component is less than 1 because after scaling each of the component would be 1. Okay, averts over. Okay, teeny terms may still underflow but can be ignored safely. Final norms is rescale and correct management. After calculating, you just rescale it. So whatever the scale in the beginning, you just rescale. Then you get your solution perfectly. Okay, when computing QR decomposition using reflectors, we apply Q equal to I gamma UUT, where gamma equal to 2 by U norm of U2 square. So, and now you see this when a B, say any matrix, the B is the size is n by m. Okay, and this QB, Q is nothing but this one, I minus gamma UUT. This is reflector, and I am multiplying with the B matrix. Okay, And if you do multiply B matrix, the B minus gamma U UT, and you do substitute VT equal to gamma UT. And what you will get? QB equal to B minus U VT and B. Okay. Now you compute VTB. This is of dimension 1 by M. And then computer outer product is this. You will find the QB equal to B minus. First you do first you calculate V transpose B and then V. You can do both of. First you compute U V transpose and V, and V transpose and V. So both the way you will be getting different class. In one multiplication you get more flops, and one kind of multiplication you get less flop. But multiplication you are not doing anything wrong. Okay, correct? Either you multiply U V, then B. First V transpose V and U. This differs. Okay, I'll show you. You see, if I am computing this, first U V transpose, how much flops it requires, and when you compute V T B and then U, the how much flops you will get. You know, you are not doing anything wrong in multiplication. You are following that. But one way you are getting more flops, in one way you are getting less flops. So you have to take the less. So you check this. U V transpose. This is all of n square. Because why? That U has n components. V has n components. You do multiply. N addition will be. So this is n square. You know, because only multiplications are there. This is n vector, you are multiplying this. Okay, n square plus. Multiply with the b. Okay, and this cost to 2n square m. Why it is? Because it is already n square plus, and you are multiplying with the b. Because b has n by m. You just multiply first, then you multiply second column, then you multiply this, then the last m columns are there. Is not it? And then 2n square m. Because m columns 2n square m plus. And total cost is 2n square m plus. Okay. You remember how much cost this 2n square. Now you see the second part. As I told you, you take this multiplication. First you multiply this one, and then you. The V transpose V, it costs nm plus. You just recall. What is the size of this matrix B? N by m. M columns are there, and n rows are there. And what is the size of this? M. And you just multiply the first column, second column, third. So in one column you need 2n plus. So n columns are there. 2nm plus. Okay? You got it? Now you see, this is, you are getting nm plus, and if you do multiply u, you will get 2nm plus. Okay? Because this is also vector, this is also. You already have seen. You just add this. How many plus? 3nm plus. So earlier, how much you got? 2n square m plus. And here you got 3nm plus. Which one is bigger? Previous one. Okay. And when n equal to m, you will get 3n square plus. Is not it? And the remaining other part is that, yeah, you see. Now you have the first part you have computed. This is a 3nm plus. And this is b n by m matrix. And this another addition. Each term you are subtracting. The another nm plus. So total how much? 4nm plus. Understood my point? So earlier you have 2n square plus. Then again you are adding something. Nm plus will be there. So it's more than this plus, the 4n. And if you have, say, n equal to m, it is 4n square plus. So how it acts like this? Already you know that first q is when you multiply with this reflector, you will get 4nm plus. The A is the matrix and q is there. Okay, and the q transpose is there. So A is the matrix, say R n plus n, n plus n. And this is the reflector. How would it reflect? I minus gamma u transpose. And this is transpose. And this is it. I have taken there B. This is same thing, it is working. Okay. So forget about this. You just take this. How many plots you require? This you require 4 and square plot. Yes. And after multiplying, you are getting this. Star and 0. Yes or no? Rest of the entry? Yes. Already you are clear that first operation you need this 4n square plus 4n square plus by this. We are not going to take the first one, we are going to take the second one. So once you have done, this is the size of the matrix n minus 1 by n minus 1. Okay. And you do process similarly. So for this you got 4n square plus. And here, if this is your vector, and this is the size n minus 1. And then again you calculate this, this say for example, this is your Q1, okay? And then you get the Q2 filled up. And this is the size is I minus gamma. And similarly here U is say U and U transfer. But the here U size is n minus 1. That makes sense. So once you got this, then you get Q2, this 1 and 0, 0 and this Q2. So this is also a whole. That may come. So once I got this 4n square plus, and I am constructing any of this sum matrices, then I got this. Okay, and this is the orthogonal matrix, and its size is n minus 1. So when I make this one, because one side was less, say 1, 0, 0, and Q2 transfer, you just put this, and you get again orthogonal. Okay, and similarly, if I go back, I got this Q2 transfer, Q1 transfer, and then here you got already this, the first column, and this is 0, and this is star, and 0, 0 you got, and the rest is as it is. Okay, this is non-zero entry that. Yes, sir. So once I got this, I have to work on this. Yes, sir. And this is the size is n minus 2 by n minus. I process same way. Again I construct this is I Q3 till the transfer. And I will find this my detector. I minus gamma UUP. And my gamma is always like 2 by norm of U norm 2 square if it is not normal. If it is normal, that is 1. Okay. So once you do this, so what is the size of this? This is the size is n minus 2 by n minus 2. And this is orthogonal. So I can construct Q3, which is like this. First you take 1, 0, 0, and this 0, 1, 0, 0, and then you substitute this Q3 theta. Okay. So I got this another orthogonal matrix. So likewise, I can generate all n minus 1 orthogonal matrices for which I'll get the upper triangular matrix. So just because the first operation equals 4n square plus. So similarly, the second operation 4n square, the second one takes 4 into n minus 1 whole square plus. Because first one takes n square plus means 4n square, and so on. It will go up to 4. Okay. So 1 square plus 2 square plus that n square plus. Yes. This 4 into n plus 1 into 2n plus 1 divided by 6. Okay. Yes, sir. So what once you got this, you do calculate, you will get 4n plus some other terms are there. If n is very large, we just will take this 4 into by 3 plus. Now you recall the first one you got in LU, you got how much? 2n cube by 3 plus. And for Chomsky, how much you got? You got n cube by 3 plus. Okay? And for the Q1, how much you got? This is 4n cube by 3. Clear? This is much more expensive. That's it. You are multiplying in the same way. as you do the multiplying. But here you have seen, first you are multiplying and you are multiplying first 2 and then multiplying 3, then there is a difference. So complexity accordingly you can change by using this calculation also. Okay, and there is a theorem. It says that there exists unique Q and R. Always, if a matrix is n by n matrix and it is a non-singular matrix, always you have a unique Q and R such that Q is orthogonal matrix. This is one way reflectors, rotators you are making. Similarly, when you do gram symmetry process, exactly you are doing the QR. And in gram symmetry, you are doing QR. Because if you have linearly independent set, you are orthogonally, and there are many multipliers. Say, for example, multipliers in the LU decomposition you have seen, and those multipliers give you unique lower triangular matrix. You have seen. Same thing in gram symmetry process, you are doing the multipliers, okay? And that multiplier will give you the upper triangular matrix. And Q is orthogonal matrix, you find this one. Okay, this is unique because if you do small calculation, you can find this uniqueness if you define dii equal to sine of rii tilde, and because all these diagonals you are making the positive. Okay, q equal to q inverse, because r d inverse, if you do multiply like this, that's r would be the upper triangular matrix, whose diagonals would be non-zero positive. So once you have this, then you have, by using the Cholesky factorization, you will get QATA, you will get immediately R1T R1, because this is the symmetric and positive definite matrix. Then you have the Cholesky factorization. And if the Cholesky factorization is unique, that means R1 equal to R2, that means EQ equal to Q1 equal to Q2. Okay, because Cholesky factorization gives you uniqueness, and from here you will get this one. Okay. And here is the MATLAB code, because everything you can calculate through your MATLAB, whatever I have discussed here. Say n equal to 7, a equal to just take the random n, and just in the, this is the MATLAB code, QR equal to QRA, and it will give you the Q orthogonal matrix and R upper triangular matrix, for which you will get the Q and R equal to A. And if you just calculate the transpose star Q and norm of this one and this, you just check whether it is accurate or not. Okay. So if you reflect us, if you do Q transpose Q or A equal to QR, if it is coming perfectly fine, that means it is good, even for the ill condition matrix. Okay. And this is, you can see norm of A minus QR is very less than 1, very small quantity, and that means this is the correct. And this entries on the diagonal of R are not necessarily positive, because in case of QR decomposition it is not, but when you prove the uniqueness, you can set R as a with positive diagonal entries. The MATLAB doesn't enforce this by default. Positive diagonals are needed only for uniqueness. Okay. In general, when you do compute QR factorization in your MATLAB, you won't find that R all the diagonals of entries of R matrix would be positive. It may be different sign. And for the help menu, you just go a help QR, you get this, and similarly you go to MATLAB, you help LU, you find all the information of LU. Likewise, you have this. Now we will be talking about the stability, whether this method is stable or not. How you know that QR decomposition is stable? It's stable in the sense is that when you do calculate, we have to find the floating. Yeah. The floating point error and the rounding error, from there you can decide whether your number, whether your calculation is correct or not. Say, if you put any numbers in your MATLAB or in Mathematica, you won't expect exact number. Say, for example, if I put 1 by 3 in your MATLAB, it won't get the exact result. It will terminate somewhere. Okay, 0.333333 go like this, and it will give you some fixed number as per your machine's capacity. You know, but we are losing error. Yes, we are getting some numbers with fixed epsilon. Okay, this epsilon is the error, and how much error you can allow in your calculation, that is important. And sometimes it is a big number, sometimes it is with the rounding error. If it is about rounding error, then it's okay. That is the machine error and the calculation error, all such things that you can use. So here is the number, say fc equal to say if you do calculate, what you get this 1 plus epsilon into c. This epsilon will get error. So instead of number c, your computer will recognize 1 plus epsilon into c instead of c. This floating point of here is floating point of c. Floating point number. Okay. That way. So similarly, this is the floating point of the QA. This is QA tilde means this means I'm asking you floating point of QA. And this would give you Q of A. This is A plus C. Okay. If I put my number, say X is a number, and Y is a number, and Z is a number, if I put in my MATLAB, it will calculate not X, it will calculate X, get Y, get Z. Agree or not? And this number says floating point of X, I am writing that is 1 by X into 1 plus X. And this epsilon is less than unit round of error. This unit round of error, it depends for the single and the double. If it is single double 32 bits or 8 bits, and accordingly your rounding error will become 10 to the power minus 8 base to the 5th, and for the double 10 to the power minus 16 base to the 5th. So accordingly you can decide how much error whether this is as per your rounding error definition or. So similarly here you see, if you put QK, this is the floating point number, the calculation, this Q and A, and it will calculate Q into A plus. Instead of QA, you will be getting Q into A plus E, where this is a relative error and this is very small. Okay, and this is very small means this is order of rounding error, unit round of error. This order of U. Okay, small number means order of U. It depends on you what kind of calculation you are doing. So the computed result is the exact result for a slightly perturbed input. It means like this. Okay. And now you see, if you have, say for example, Q1 you have multiplied, again you are multiplying Q2, then you have to calculate the floating point error of this. What you did that every time you will getting for E the error, and it's this. What is E? The Q1A, first you will calculate Q1A, Q1A plus E1, and then again you will be calculating with the Q2, and that this multiplication. So when you put 3 numbers in your computer, say W1 plus W2 plus W3. So what you do, first you multiply this, add this, and then this. Similarly, Q1 and Q2. Q1 and Q2 is there, and first you are doing this, and then you are doing this. For this you have error. For this you have error. Okay, the first one you got the Q1A, this Q1A plus say E1, and the floating point. And then you have this Q2, Q1A for this, and this floating point of this one. That means floating point of first this Q2 and this Q1 A plus E1 and this is again equal to FL, and if you remove this floating point here at Q2, Q1, this A plus E1 and this is plus E2. And where E1, this norm of A, this is less than equal to unit round of error, U, and also E2, norm of A, this is also less than equal to unit round of error. This is the way we calculate. And first you calculating Q1 with error, and then again you have error. Yeah, the first error you got this one, and the second you got this. So calculation is this: first Q1A and the Q1A plus U1 you got. Again floating point. That means the floating point of this Q1A, again floating point of Q2 1. So like this you got this. So same thing U1, Q2, U1, E2, you just get this one. And you just take this as a E, Q2, U1, and you take the norm of this one. Because here is Q E equal to this one. Okay? E equal to E divided by A norm. This is, if you have say Q2 E1, this is equal to Q2 E1 plus E2. Yes or no? This is norm divided by norm of E. Okay? This is less than or equal to, this is norm of E1, norm of A, and this is E2, norm divided by norm of A. And this Q is orthogonal, so its norm is 1. So I am not using this is of unit round of error. Okay? And this is also unit round of error. Is not U of order of U. And this is order of U. And this is order of U. Okay. So my matrix multiplication, whatever using by QR factorization, we are getting the unit round of with this calculation. Say for example here 2, Q2, Q1. Again you do multiply Q3, Q4, Q5, Qn minus 1. And you proceed like this. At the end you will get norm of E divided by A. You will get very, very small number, and which is called teeny tiny number, very small number, and which is around to unit round of error. In that case, you can tell your number is stable. Otherwise, you get it. Understand? Now, both givens and the horizontal transformations are non-wise backward stable. Error accumulates slowly, and this is remains small. Remains small. And QR decomposition using orthogonal transformation is highly reliable and numerically stable. Simply QR based methods are robust and suitable for solving the least square problem. Okay. So why would I want to convince you that the QR decomposition we are going to use to solve the least square problem? Okay. The before applying to solve the least square problem, so one has to know whether our method is stable or not. So without knowing, if you solve the least square problem, unstable algorithm, if you put and you get wrong results. So that's why every time I need to tell there are many decompositions are there. So the one you are using is backward stable. So here we have seen that QR decomposition is stable. And similarly, if you have a real complex real rotators, and also you can have for the complex rotators also is there, and you can apply this technique for the complex matrix as well. And this says that if you have this given xy, and these are the complex number and their norms are the same, and this xy in R2 say there exists unitary q such that q equal to I minus beta u transpose beta beta is a complex number and u is a complex vector, and such that qx equal to y. The earlier version what I told you for the real cases, and similarly it is true for in the complex case. Also you can show the uniqueness of this QR decomposition. So these are the, you can check this for the complex matrix. You just take this any random matrix N, and with this is the MATLAB notations, MATLAB programming, and the Q are just you put this and just you find this Q and Q transpose and just check the I minus Q this is around unit round of error or not. So this difference should be around to 0. So because Q transpose must be equal to identity, and the difference with the norm should be equal to this one. Okay. And Q is a unitary matrix for the case of complex, and Q star Q equal to identity. Q star means complex conjugate, and this is approximately equal to QR, and it's a small residual. Okay. MATLAB handles complex matrices. So now I was talking about, previously I talked about the square matrix when A is a non-singular. Q are also applicable for the non-square matrix. As I told, to solve the least square problem, you can apply the QR method for solving the X equal to B, whether when A is a overdetermined or underdetermined box. Okay. So A is this matrix is n greater than equal to m. And A is the orthogonal matrix, this one QTQ equal to 1, a matrix R of this form, this R cube. Say for example, if it is a matrix and it's a rank, maybe n, maybe n, it may have full rank. Okay, if it is a full rank, then R would look like this. Instead of full upper triangular matrix, you would be getting R cube, where R cube is an upper triangular matrix. And R cube is a square matrix. It depends on the rank of the matrix. If the rank of the matrix is, say, for example, R, and this R cube would be R. And if it is a full rank means if the rank of the matrix is M, then R cube would be of size M by M. And this is the full rank matrix, and it would be non-singular because it has M linearly independent vectors. Okay, so likewise you can form the A equal to QR for a non-square matrix. Okay, but here Q is, you see, orthogonal matrix, it remains square, but R is a non-square matrix. Okay. Now, as I told you, to calculate this flop counts of this for the non-square matrix, as we have calculated that this is 4n cubed by 3 when n equal to m. And if you do substitute n equal to m, you will get 4n cubed by 3. So this is the general method for non-square matrix. For non-square matrix, the flops for getting A equal to QR is 2nm square minus 2 by 3 n cube when the size of the matrix is n by m. Okay, and if you do substitute n equal to m, and what we got in our slide here, board 4n cube by 3, you can just 2n cube minus 2 by 3 n cube, this is 4n cube by 3. Okay. Now this is the calculation. Again, I have given you in the board that you can keep this as a. Yes. Now I am coming to how we are getting to solve this equation when minimum Ax equal to b is there. So let's see here better. Suppose you need to solve the X equal to b by using the QR factorization, the Ax equal to b is there. And you want to find this this is minimum over X, okay, minimum over X and Ax minus b. You have this, okay. So if lower A equal to QR, okay, then norm 2 equal to minimum of X, norm of this Q and R, X minus B. Okay. I will take this minimum X and take the Q common Rx minus Q transpose B. Okay. This. Here, and this is X, and this norm it can go out. Okay, and its norm is 1. Okay, I can put Rx, and this is my C, another vector. I can put where C equal to Q transpose. Okay. So what I did is that on this full matrix, why I got this R matrix where R is the upper triangular matrix. So half of the entries we made into 0. Okay, by using the QR factorization. You see, A equal to QR and QRX minus B. As I told you, the two norm and the Frobenius norm are invariant under orthogonal transformation. So Q norm is equal to 1. It can come out. So now Rx minus this is C is a vector. So instead of solving this X minus B, you are now solving Rx minus C where minimum X is there. So here C inside the rank usefulness. If rank of this matrix is the rank of R, that means R equal to Q transpose A. And by the linear algebra technique, you have the rank of R is less than equal to rank of. You know, this is one of the really important. And A equal to Q, R rank of A equal to less than equal to R, therefore rank of A equal to rank of R. This is the proof, a small proof by linear algebra technique. If AB is there, then you have this less than equal to rank of A and this is less than equal to rank of R. And finally, you have seen that rank of A equal to rank of R. So if you do have orthogonal transformation, say A equal to QR, the rank of the matrix R is nothing but the rank of the matrix is. So A has a full rank, that means R is non-singular. Okay, because R has a non-singular matrix or it is immaterial. Now you see, suppose this matrix is suppose A has a full rank, first you have, and sometimes you may not have the full rank also, overdetermined, underdetermined, and in that case you will get the infinitely many solutions. Infinitely many solutions if it is overdetermined. But if you have the full rank, the least square solution would be unique. Full rank, if it is full rank. Otherwise, it is infinitely many. This uniqueness, if it is a full rank matrix, and then the least square has a unique solution given as this following: R cap x equal to, as I discussed here, Rx minus C. This is R cap x minus C. Here is same. And that is R cap.
In that case, how will we write that R is writing column R cap 0. So if it is rank is not full rank.
Yes, if it is, say for example, if it is not full rank, say rank of this matrix is R, and rank is A matrix is R, and R is strictly less than minimum of Mn. Then you will get matrix, say this matrix, you will get Q and R. For QR, what you will get, and this R would look like something, this R cap, and this is 0, and this is the size of R by R. That means you will be getting the R cap C. This means the unique solution you are getting X, but or the rest of the entries are 0, but this R terms are fixed. Isn't it? That means X, you have this X equal to this X1, X2, up to Xi. Yes. This is coming from, because the R cap is non-singular. It has unique solution. So this will be fixed. There won't be any change. But this is the free variable. There will be free variables. Anything you will put, that will be the solution. So that way you will be getting the infinite dimensions. That way. So this is the reason why. Once you will apply the QR, and then you are getting R cap 0, and then R cap C inverse decay, because this is a non-singular. If it is non-singular, then you have unique solution. And if it is unique solution, the length of this vector is R instead of N, say. Okay. Then it is for R term, these are the fixed, because these are unique, and the remaining you don't have hold. You cannot get one. Yes, sir. Yeah, please.
But then it is like that R is if R is R cross R matrix.
Yes.
R cap. Then R is R. It will be M into R matrix.
Yeah, remaining, but first one would be, this would be square matrix. This would be square matrix. Say if it is, if you have R, rank is R, then you have. I think I have put some, no. You can have this, okay. So. Yes. This R you have, this R equal to, what is the size of this R? If A equal to size of this matrix is n cross n cross n, and n is, say n is bigger than n. So if you are writing QR, Q would be square, Q would be square matrix. So what would be the size of this matrix? N into M or M into N?
Into n.
N into N, say N into N. And this would be N into N. Yes, sir. So if it has a full range means this it should be M, say. So up to this, you have this R, the depth of the entries, this will be 0, 0, 0. And this is the size is N by. And this is my square matrix. Remember. So once you got this, your R will look like this. Instead of full, instead of this, it look like this. Here is the upper triangular T is there. This, and this is 0. That my point. So by using this square, you can get the solution. Over. Time over. Okay, let's stop this here. And if you have any questions, you will see. So these are some MATLAB code. You can calculate. Say for example, m equal to 5 and m equal to 3, and you just put a equal to random n by m. This is m by m matrix, and you can generate this, and b equal to this one, and just you apply this R full whatever we discuss here, and this 1 by m. So this matrix is of size. If it is m by m, you just extract this, and you just calculate, and you get this residual norm H minus B. Okay. Thank you so much. If you have any further questions, let's know. Yes.
Sir, in the word
Yes.
Good morning, sir. My question is from QR decomposition. We take A is equals to QR, where Q is orthogonal and R is upper triangle matrix. So it is always that R has a positive diagonal entries. R also can take 0 elements.
Yes, R can take 0 elements. It depends on because the 0 means already 0 are there in the R. Okay. R, most of the entries are 0 because upper triangular matrix means 0 or 0. Okay. Now the question is this R here means if it depends on the rank of this matrix. If R means non-singular R, okay. Here R you are not getting non-singular. You are getting the first part. This would be look like this. This is upper triangular, and the rest are 0. So this is non-singular, okay? But these are the 0. Okay. So 0 is there in R.
And the second question is from least square. We always do the minimizing curve. If we take, instead of discrete data, we take continuous data like straight line, curve fitting, like summation I is equals to 1, 1.5. So it is also applied for continuous data?
Yes, it is applied for the continuous. Continuous means if you have discrete, whatever we are discussing, summation you are taking all are discrete.
Yeah, 1 to n.
Yes. But if you are going for continuous, then integration will be.
Okay, so and the last question is reflection matrix. we always take norm of u, norm 2. We also can take norm infinity, norm 1.
Yes, you can take.
Okay.
So instead of that, you can normal 1 to infinity. But most appropriate is 2.
Thank you, sir.
Sir, what do you mean by numeric? What do you mean by numerically stable of rotators and what?
Yeah. Because when you do compute your rotators and reflectors, sometimes it may go overflow and underflow. Okay. It may overflow and underflow. In the sense that, as I given one example that it is underflow about 10 to the power minus 10. Okay. But each of the entries of the x is around 10 to the power minus 10. Okay. If you find the true norm of this vector x, it would give you 0 instead of some non-zero numbers. Okay. So in that sense, you can take this numerically unstable, because you won't get the result. Okay. This is one way you can take. And the second, the numerically stable means in all these computations, as I told you, if you put any number in the computer, instead of exact number, you getting it number with error. Okay, that's why I have used the floating point. So if you do compute your solution with error means with the floating point error, and that much permits. That means if you can able to do this, that means you are doing everything to the numerically stable way. Otherwise, that is a problem. Because the errors you cannot control. If it is beyond the unit round of error. If it is machine error, it's fine. Machine always gives error. But that error should be minimized. And IEEE standard error is that one it is permissible. The one maybe I can discuss something floating point error if I get some time for the how it affects in calculation. So numerically stable means, in other way, in our last class we discussed that if you small change in the input and its relative error would be small. If you are changing small and the error would be small. And if you are changing a small number like the last class we have given 0.0001 and the solution was 1, and if you change a small, you get 2 and 0. So this is numerically unstable. And another example I gave you yesterday, well condition, if you are giving a 0.01 and the error is reflecting same, with the increment 0.01. That means this is stable. It depends on your calculation. It depends on your matrix. It depends on your data. Clear?
Sir, does sensitivity of a matrix has any effect on finding keyword decomposition?
Yes, of course. Because it affects, but QI decomposition, it is not like the any decomposition. Because any decomposition, it is we have seen the instability there by giving some examples I have given. But as we have proved for the stability, and it follows the definition of floating point error, the QI decomposition. As you have seen, the Q1 transpose A equal to with the floating point error plus C. Any number floating point x equal to x into 1 plus epsilon. Epsilon is less than unit number. And that calculation follows QI decomposition, as we have seen. That means it follows the standard method of stability. The one which is scientifically proved that this much error can you can allow for the computation. Beyond that, it would be huge error and because you have a lot of calculation into having multiplication. If small error if you are getting into loads here. So each calculation, first calculation we have multiplied Q1 transpose J, we have seen that this is the satisfied unit downward error. And the second matrix we have multiplied, remember, QT and Q1, still it is following that condition. Again, if you multiply 3, again you will find that condition will be satisfied. You know, every time I am checking, you know, it is not like that. In one multiplication, you are getting unit downward error. Again, if you put second multiplication, you won't get. That means your method is not stable. Understand? Each and every point you should get. That means.
Thanks.
Any other? Thank you so much.
On to topic of the last presentation.
Second.
Goal function of GNN model is defined as Frobenius norm of error function. We spoke about this choice. We spoke that Frobenius matrix norm is defined using matrix trace, and we have well-known derivatives about matrix trace. Because of that, Frobenius norm is preferable matrix norm in optimization. Second step of GNN model assumes the relation between time derivative of unknown matrix V of t and the derivative of goal function with respect to unknown matrix V. We can consider such derivative of goal function as gradient, and in that way, GNN design represented in one is kind of nonlinear optimization methods. Precisely, GNN is based on gradient descent nonlinear optimization methods. Because of that, we have named gradient neural network. Gamma here is a scaling parameter, which should be as large as possible. In our numerical experiments, we try with smaller, with bigger parameters gamma, and observe that bigger values of parameter gamma leads to faster convergence. Theoretically, gamma should be chosen as large as possible. Here is a verification that gradient neural network design is a kind of gradient descent neural net, gradient descent nonlinear optimization method. We used first Euler forward difference rule and made the differentiation of time derivative of unknown function V of t. In that way, we obtain kind of discrete nonlinear gradient descent nonlinear optimization methods. Here, parameter beta is defined as multiple of small parameter theta, which represents something time, and big parameter gamma. We will consider now with more details. GNN model aims to solve a linear matrix equation AXB equals B. X is unknown matrix, A, B, D are given up matrices of upper dimension. As usual, we found the error matrix replacing X by V of t. Goal function is defined as square of Frobenius norm. We found the gradient of error of the goal function using the matrix calculus, standard matrix calculus, and obtained the GNN ABD model in this way. This formula will be investigated for future, and because of that, I will write this formula here. Derivative of V equals to gain parameter gamma A transpose B minus A V of t B, B transpose. This model we will call GNN ABD. Convergence defined by this moment, by this design is infinite. So in infinite time, V of t converges to exact solution tilde V of t. Because this solution is dependent on initial state, we will use here V of 0 index. If you remember yesterday, we made some numerical experiments and changed initial state. According to initial state, we obtained different results. Because of that obtained result, we will mark by V of 0. Here is first result about convergence analysis. If we want consistency of linear matrix equation AXB equals B, then condition in form 5 must be satisfied. We saw that this condition is not implied by GNN dynamics. It is the theoretical requirement from GNN model. If this condition is not satisfied, then the linear matrix equation AXB equals B is not consistent. If condition 5 is satisfied, then AV of T times B converges, then time converges to infinity to exact solution B. For arbitrary initial state matrix. Here we will verify proof of this statement. Verification of this proof is useful to show requirement of nonlinear optimization. We thought that for nonlinear activation function must satisfy two properties, must be odd and must be monotonically increasing. Here in this proof we will see why these two properties are important. We consider arbitrary inner inverse of A and arbitrary inner inverse of B. And suppose that solvability of matrix equation AXB is satisfied. It means that we suppose condition A1 B A1 B equals D is satisfied. Then we consider substitution defined in this way. V of t is overlying V of t plus A1t B1b. What will be differentiation of function overlying V of t? Overlying V of t is defined as V of t practically minus A1 V A1. Derivative of overline of t by t is the same as derivative of v of t by t. Why? Because second term is constant and the derivative of second term will be zero. It is v dot of t, and according to GNN model, v dot of t is equal to gamma A transpose d minus A d of t d d transpose. Now we need to replace v of t using this replacement rule. Here instead v of t we will put overlying v plus a1 t v1. If we consider non-linear model, here will appear calligraphic a function which assumes that element phase applications of odd and monotonically increasing function. Then we will obtain gamma A transpose calligraphic F of d minus A v of t is replaced by v dot of t plus A1 d A1 d after that d transpose. Perform multiplication here by A from left and by B from right. Then we will obtain here term A1B, B1B, which is equal to B, according to solvability of our linear matrification. If future leads to too small space to write overline v of t derivative by t is equal to gamma A transpose nonlinear activation v minus A v dot t A v dot of d minus v B transpose. D and minus D are cancelled, which leads derivative with this to T is equal to minus gamma A transpose calligraphy F A overlying D of T B B transpose. Which is formula 7. Then we need to define the Lyapunov function candidate. It is typical approach how to verify convergence of recurrent neural network or convergence of the dynamical system. It is necessary to define the Lyapunov function candidate and then verify some special behavior of this Lyapunov function candidate. Typically, a Lyapunov function candidate is defined using Frobenius norm again, because we will use derivatives with respect to Lyapunov candidate. L of P shall equals 1/2 Frobenius norm of overline V squared. It is according to definition of Frobenius norm, trace of overline P transpose of overline P. Clearly, Lyapunov function candidate is non-negative function because it is defined using Frobenius norms, value of Frobenius norm, it is non-negative function. And now we will use derivative of Lyapunov function candidate with respect to time. And such formula based on the derivative of matrix trace will be applied. We obtain derivative of Lyapunov function is, here is formula I will give shortly, it is transpose and then derivative. Transpose times derivative, that trace again, transpose derivative. But we obtain formula for derivative of V dot, here is applied here instead of derivative of overlying V. Here is derivative of overlying V. And use the cycle property of matrix trace. BT goes first. Again, I will repeat it. It is not because of commutativity of matrix trace. It is because of cyclic property of matrix trace. Then B transpose another matrix transpose is, you know, this property, AD overlying B transpose F of the same matrix, nonlinear activation of the same matrix. We obtain what we want, just what we need. One matrix transpose and then nonlinear activation of the same matrix. Practically, if calligraphic F is linear activation, then we will have matrix multiplication of transpose and usual matrix. In any case, this derivative is less than zero. And can be zero only in case if matrix A, B, overlying B, B is equal to zero. In all other cases must be zero, if we consider linear activation. What if we consider nonlinear activation? Here we must apply odd property of nonlinear activation F. It means that calligraphic F takes negative values for negative values here. Positive for positive values here. And try to apply increasing, monotonically increasing properties. Because here we will have bigger values after application of nonlinear activation function. To make consideration easier, we make one replacement. A overlying B will be not shortened by W of P and obtain this more readable formula. Element-wise, if we define a matrix trace, we will obtain such formula. And because of properties of and monotonically increasing of function f, we will obtain that derivative of the Lyapunov candidate function is less than zero if function W, if matrix W is different than zero matrix, and equal zero only if this matrix is equal to zero. According to Lyapunov stability theory, matrix W of T defined as AW B minus B globally converges to zero for arbitrary V of zero. It is typical approach how to verify global convergence of dynamical system. We need to define the Lyapunov function candidate and verify such two properties that the derivative of the Lyapunov function candidate is less than zero if underlying matrix is different than zero and equals zero if this underlying matrix is zero matrix. If we want to generalize this to tensor case, we will need to introduce a derivative of tensor. What will be Frobenius norm of tensor? Three-dimensional. If we have definition of derivative, then it will be possible to verify global stability, global convergence. It will be necessary to define the Lyapunov function candidate. Typically, the Lyapunov function candidate defines as defines as square of Frobenius norm. We started from Frobenius norm in defining GNN dynamic, but I again use Frobenius norm to define the Lyapunov function candidate. Second result, also very important. From my opinion, better than previous result, is about the result of convergence. This theorem says what we can expect after convergence. First theorem which we presented is classical result. It is classical approach, define Lyapunov function candidate, then use derivative of Lyapunov function candidate and analyze behavior of this derivative. This approach was new before this publication. And there is one very important property 13, which says that final result tilde V0 given as limit of V of t with respect to t when as t tends to infinity is equal to A dagger B dagger plus arbitrary matrix in theory. Arbitrary matrix in theory, here initial state minus A dagger A V of 0 B dagger. Very important result. It means that V of 0 corresponds to arbitrary matrix which appears in linear algebra theory. Usually it means that if we change V of 0, we will obtain different risk-based solutions. Here is one is comparison with the theoretical solution. Theory says that such expression with arbitrary matrix Y satisfies this inequality and set of risk-based solutions that represented in form 15. Evidently, norm of the Morgan solution is smallest between all risk-based solutions. Because of that, Morgan solution is so-called minimum norm risk-based solution. Shortly, we will say best approximate solution. Because of uniqueness of Morgan's inverse, Morgan's solution is the most frequently used. Here is proof about this result. This result says that arbitrary matrix from linear algebra theory is replaced by initial state matrix. Here is verification. We consider matrix V1 of T defined as A target A B B target. Here not possible to use arbitrary inner inverse instead of Morphenau's inverse. For simplicity, we use Morphenau's inverse here. And then we ask the derivative of V1 of t with respect to t. It is equal to A target A derivative of V of t, B target, future equal to A target A. Here is V of t, gamma. I will put gamma in first place. A transpose B minus A V of t B B transpose D B target. And now we use well-known properties of Morphenau's inverse. Familiar with theory of generalized inverses can recognize this formula. Transpose B target is equal to B transpose because B target is projector to a range of B, if you like theory. A target A is projector on R or on B transpose or A star, and A target A transpose is equal to A transpose. So here we have A transpose and there B transpose. We will simplify this formula. A transpose. It is E of t and B transpose. And it is equal to the derivative of V of t. Here is E of t. So derivative of V of t is gamma A transpose E of t B transpose, which we use below. It means that second term V2 of t is constant. Anyway. We define V of t, V2 of t as depends V of t minus V1 of t. This matrix must be constant because derivatives of V of t and V1 of t are the same. Derivative of V2 of t is 0, which means that V2 of t is constant and V2 of t in arbitrary time instance must be the same as in initial state. It will be equal to V of 0 minus V1 of 0. V of 0 is steady, V of 0, and V1 of 0 is equal to this one. And in that way, you obtain second term for convergence. Here is more Penrose term, or we can say here is best approximate solution term, and here is another term, V1 of 0. Sorry, it is second term, V2 of 0. So we intentionally define matrix V1 of t in this way. We expected multiplication by A from left and expected multiplication by B from right. Then V of t is equal to V1 of t plus V2 of t V1 of t is Moore-Penrose solution A dagger D, B dagger, and V2 of t is constant and equal to V2 of 0. Here is the definition of V2 of 0. And in this way, you obtain this important result. Was not easy to verify this result first time. Even now, after many verifications, I have problem to go in all details. Here is one corollary obtained after two theorems. This corollary says that multiplying obtained solution by A from left and by B from right for arbitrary initial state V of 0, we will always obtain the same result. These solutions, all such terms are solutions. We can try, is no problem. A tilde equals 0. B is equal to A dagger B dagger B plus A B of 0 B minus A dagger A, which is clearly A B of 0 B dagger B, which is clearly B. And then this term and another term will be cancelled. Here we have term A dagger B dagger B, which is according to assumption equal to D. Yeah, I must go there. We had this assumption about consistency. A dagger D, B dagger B is equal to D according to assumption. We can change method, we can change algorithm, but always this condition for consistency, the consistency will stay. After these transformations, we can clearly observe why this condition is necessary. Because after multiplying by A and by B, from left and right respectively, we obtain such term A dagger D, B dagger D. And if this term is equal to D, we have solution. If not, no solution. We can try, but GNN models give some kind of solution, some kind of approximation. They can continue or something. It will not be, of course, exact solution. ADD will not be exactly D, but will be some approximation of D. In any case, we can use ZNN model, another, we can use iterative methods. Inconsistency stays always. So, if we multiply arbitrary obtained solution, arbitrary obtained solution means solution obtained from arbitrary initial point. We will obtain the same result multiplied from left by A, multiplied by B from right, obtain solution that always will give exact solution. Now I will prepare say something about future presentations and about future tutorials which we will have. Here will be more results about nonlinear activation function. We spoke that nonlinear activation function, calligraphic F, assumes element-wise application of another function, calligraphic F. Usual F. Calligraphic F is matrix function. And this calligraphic F, nonlinear activation matrix function, is applied element-wise to matrix C. If matrix C is with such entries, then F of C is defined as such matrix also, where F is monotonically and odd activation function. We mentioned the list of most important activation functions: linear, bipolar sigmoid, power sigmoid. There are several parameters which change approximately. We made some numerical experiments and compare linear model with nonlinear model, and observed the faster convergence of nonlinear models with respect to linear one. Also, we may make comments, comment that increasing gamma leads to faster increasing of convergence than use nonlinear activation. Here is a list of two finite time of two activation functions which lead to finite time convergence. It means that we apply such two nonlinear activation functions. We can define time in which convergence will finish. We can continue with the future, say, with GNN model, but result will stay the same. Here is graph of main activation functions. Small power sigmoid, bipolar sigmoid function, linear function. That is a linear function. And these graphs clearly show properties of nonlinear activation. Clearly show that such activation functions are odd, symmetric with respect to center, to cross of coordinates, and all nonlinear activation functions are monotonically increasing. Here, for today, I presented a list of some additional activation functions now in literature. Even this list is not complete. Many researchers devise new and new activation functions. Sine function is one activation function. Why? Because sine function is odd, monotonic, and increasing. It is one of first activation functions. Here is MATLAB simulant implementation of MATLAB, because MATLAB has block for sine function. We can only use this block. Here is Lie activation function. Enables finite time convergence. From my opinion, it is first and best nonlinear activation function which resulted in finite time convergence. What is important to mention here? Here is one small power with respect to u, and another one is one big power, because u is between 0 and 1. And it is desirable property of finite time convergence. Don't allow, if you use only one power, then when the error function is smaller, we will have here smaller and smaller values, and gamma in front of this error function will be bigger and bigger. Because of that, we here have one small and one big. Opposite is if u is small, then first part is small, another one is big. Always one of them is relatively big, another one is relatively small. After that, many, I can say many nonlinear activation functions have been proposed. Here is tunable activation function. What is new here? New here is term in middle, which is absolute value. Tunable according to this term in middle, we can make tune of behavior. versatile activation function. Why? Because here is another plus, and finally here is one result, which make the authors. Yes, it was published. What is interesting here? Interesting here is some of such terms with power to k. Another is some of terms, and according to number n, we can predict finite time convergence. If such nonlinear activation enables predefined time convergence. According to wanted time, we can choose how many terms of this form or another form we will use. So, conclusion about nonlinear activation functions is, as we spoke yesterday, no best activation function. Always can be better. Many activation functions future including exponential term to enable faster increase of gain parameter. Many reviewers in journals ask why to use nonlinear activation. I can increase gamma as I want, as I will obtain convergence. I have such question for that reviewers, but reviewers are always right. Trying to use nonlinear activation function to achieve in right time. Yes, if we don't use nonlinear activation, gamma must be infinity to obtain convergence. Infinity in computer science is impossible to achieve. But using such activation function, we can define time which we want for convergence. Increasing number of elements here, there we can say what is drawback of this approach. Computations are more and more difficult. We can have more elements, plus, and it is applied to each element of matrix, and computation are the linear case. I will show only this figure, and here we compare several finite time convergence activation functions. For each activation function, you can see finite convergence to zero, and convergence to zero. Of course, best one was the last one, more complicated, shortest finite time convergence, reactivation function. First finite time activation function is slowest in the end, because the researchers later tried to define better activation functions, obtain better and better continuous time. Which is what we hope.
Thank you very much.
Is time.
Thank you very much. Professor Pedrak, for your wonderful lecture. So now we have some questions from viewers.
While defining the Lyapunov candidate, is it necessary to take the half norm of Frobenius norm square? Can we define any other based on our design or model?
Last question, if I understood correctly, about the Lyapunov function candidate. This in this paper and in other papers also, the Lyapunov function candidate is defined as square of Frobenius norm. By Frobenius norm, because we need in next step derivative of the Lyapunov function candidate. And the derivative in respect to matrix trace, which is in basis of Frobenius norm, is well-known result in linear algebra. If we use another matrix norms.
So we can add extra terms with the to further cancel out our further simplifier equation or model something. So like 1 minus e to the power t. So in addition to the Frobenius norm square, we can multiply it by worse.
Because it was squared, we will obtain 2 in front. And 1/2 is only to cancel this number 2. Otherwise, we will have to the simpler verification, much simpler verification means if we consider model for matrix inversion, AX minus E, I decided here for most complicated case. And say, even for me, after 17 years, it was not easy.
Any other question?
My idea was to split matrix V of T in 2 parts, V1 and V2. Verify that V2 is constant, and then verify that V1 of T leads to A dagger D dagger, Murphy solution, and V2 of T is equal to V2 of 0, and it leads to V of 0 in final result. Finally, we verified this yesterday in tutorials, change in the V of 0 and obtain different results.
Thank you very much. If no question, please.
We have to put here.
In this term, it is better to make derivative.
What?
Frobenius norm.
Frobenius norm is good for
Derivative.
because the trace derivatives with respect to trace.
Yeah, for other norm it is not. Yeah.
Trace of V transpose V is V transpose and then derivative of V.
Which book I will get theoretical explains about.
Book.
He doesn't look and I need to
Wrote this.
Yeah, we
I will give
upload.
you.
This will upload.
Will be in GIAN
Yeah.
book will be.
This is also coming on YouTube. Live is running. Okay.
I
And
can.
so will
give
be.
you the
Yeah, if you have some book, you can suggest.
book. We could buy it.
We have prepared.
stop
Stop.
if possible. See
Not finished. Not finished. Yes, but must say. Not finished yet, but we can. I can give you this paper.
जस्ट उसका फीड आ रहा है. हेलो. वीडियो सब ऑन करूं.
19 minutes.
वेबएक्स में शेयर कर लीजिए.
और minutes में ये 19 minutes share करते हैं.
सर मैंने शेयर कर दिया. अभी आपको जिस भी स्क्रीन पे जाएंगे पीडीएफ पे या फिर वन पे
ठीक, ओके.
रिकॉर्डिंग लगा रहा हूँ.
Where is it being? Okay. So now we'll start this tutorial. Okay. So last 2-3 class what we have discussed will implement. Okay. Yes. You must be knowing the basics of MATLAB. Yes or no? You have some idea on MATLAB or not? So we'll start from basic. Okay. Okay. So I have given you one tutorial. Just look into this. Say for example, you are going to write some programming in your MATLAB. Okay. So there are two ways. You can open this window and just it will come like what you are going to do this. Say for example,
अरे मेरे आईडी से एक काम कर, मैं तेरे को लिंक सेंड कर रहा हूँ, तो वहाँ से ज्वाइन कर। या तो हो सकता है वो इसलिए जो, क्योंकि वो दे रहा था, ये मैंने अपना लिंक सेंड करी है, तो तेरे आईडी से तेरे को नीचे। नहीं नहीं, ये और कुछ गड़बड़ लग रही है मेरे को। मैंने सेंड करा है नितेश और तेरे को मेरे पीसी से ज्वाइन कर ले वहाँ पे, तो मैंने सेंड करी है। नितेश कहाँ है? ये लिंक मैंने सेंड करी, वहाँ से ज्वाइन कर। नहीं नहीं, ये इसमें उसकी दिक्कत नहीं है, ये मैंने विदाउट उसके, तो इसमें 2 लोग ज्वाइन होना चाहिए, कि एक साथ क्या होना चाहिए, तभी जाके लाइव हो पाएगा। अरे तो हाँ, तो वॉल्यूम आ रहा है ना, कहीं का ऑडियो आ रहा है, तो मुझे वक्त दिया है। लाइव स्टार्ट हो गया, ठीक है। ठीक है सर, एक बार आप ट्राई कीजिए।
Okay, start it.
आप
Okay. So if you want to write a matrix in the MATLAB, so say for example, you are typing 3 by 3 matrix. So just you give one space for each entry. Okay, 3, 1, 2, 3, and 4, 5, 6, 7, 8, 9, 6. Okay, this is the syntax. Okay, if you don't know, you just write down this. If you want to give the semicolon, so it would be surface. Okay, if you want, if you don't give this one, so then it will be coming like 1, 2, 3, A equal to 1, 2, 3, and this is 4, 5, 6, and 7, 8, 9. Okay. This is good, come like this. Okay. So this is, say for example, you want to extract some submatrices, say for example, you want to extract A, say 1 to 2, and this is comma, say 1 to 2. So this will give you 1, 2, 4, 5. This is submatrix you will get. If you want to extract, and if you want to extract the first column, okay, the first column you will get this A, and this is column means all this one, this is column, comma. So you will get this first column, this 1, 4, 1 to 7. Okay. Similarly, you can extract row as well. Okay. So this is 1. Okay. You want to extract the second column, then you just write this A column, comma 2. This will give you second column. So likewise, you can extract other columns also. Okay. So if you have to multiply two matrix, say A equal to B, A and B is there, B is another matrix. Say, if you have this MATLAB we can try it. Okay, here MATLAB is there. Okay, so we can try from here. Say, I want to type this. Say A equal to, I can write this 1, 2, 3. This is 3, 4, 5, 6, 7, 8. Okay. So I do enter, you'll get a matrix. Okay. Okay. So I want to extract, say first 2 by 2 matrix. Say I have writing here, this is this one. You just write the column, comma. Sorry, one column 2, comma 1 column 2. Okay. So you'll get this matrix 1, 2, 3, 4. Okay. Say for example, I want to extract the first column of this matrix. So you just take A, and this is column. The column means this comma 1. That means the column means entire this 1, 2, 3 rows of the entry in the first column. So it will be this one 1, 3, 6. Okay. So likewise, if you want to get, say, last column, or you want to extract a row, say, so what you give, the A matrix, and you just write down the first row, and comma, column you just give. Okay, so you'll get this first row. Isn't it? Similarly, if you want to get this, say, here is the here I'll write this 3. This means it will give you, yeah, you just put it here 3, comma, and this column. This is it, the matrix. Okay. These are the basic things, or you can just open the exam file, and you write whatever you want. Say, for example, you want to write multiply to matrix, and you write, say, early decomposition. All these things you can purpose. Say that you want to matrix, say A is already there, B is another matrix. You just write this. Say I can write this random RANG. Instead of typing say 3 by 3 matrix, if I put this rand and this say I need 3 by 3 matrix, okay, 3 comma 3. 3 means okay. Yeah, let's see what it is coming. This is 3 by 3 matrix. Okay, random 3 by 3 matrix is this is. Let's give this rand 3. If you put only 3, what it is coming. This is also 3 by 3 matrix. If it is a square matrix, so no need to give for the column, and it will give automatically. So, and also you can try for, say for example, you are typing say rectangular matrix, 3 comma 4. So it will give 3 rows, and 3 rows, and 4 columns. Okay, the first one represents 3 rows and 4 columns. Okay, so you can extract like previously we have done. So if row and columns are same, then you can multiply. Say for example, if I multiply A star B, multiply, then some error will come. Some error will come this. Say that is A star B. B is okay. 3 by 3 and 3 by 4 is there. So again matrix I type 3 by 3, and the B matrix is 3 by 4. So row and columns are same. So 3 by 4 it is given. And so if I'll take this C matrix, C equal to say for example, I'll take this RAND, say 4 by 3, 4 comma 3. And you will get 4 rows and 3 columns. So if I multiply A star C, there would be error. This is error because A was 3 by 3 and here is 4 by 3. So that's why it is error, syntax error. So this done this. Okay. Similarly, you can add 2 matrix of same size. Okay. A plus B, just to put this and you get this. Because A plus B it is the different size, so it won't take. Okay. Say I'll give you the D matrix. D is again say RAND 3 by 3 or 4 by 3, whatever 3 by 3 you just give. And so I can add A plus D. Okay, I get this. So that means a component wise. If you addition, that means the size of the matrix will remain same. If it is 3 by 4, that matrix, another matrix will be 3 by 4. Then only you can add 2 matrix. Okay. And similarly, if you want to subtract also, you can do like this. Okay. This is matrix what you have. Now similarly, if you want to write some say LU of matrix, say for example, A is given. Say A is I am giving, and now I am making it clear because all this I don't need. I can make here clear. If I make clear, put clear, then entire window will blank. CLC, I just, okay. Okay, so entire things gone. So A equal to R A N B, say, I'm putting here, say, 3 by 3. Okay, then you will get this 3 by 3 matrix. Suppose you don't know what is LU. So what you do? You just put help LU. So here it is giving lot of things here. LU, what is LU? All the details you can see. The LU means matrix factorization, and this MATLAB function factorize the full or sparse matrix A into an upper triangular matrix U and a finite lower triangular matrix here such that then equal to. Okay. Suppose you don't know what is LU. Honest, you just put the help in. Okay. All the information you will get LU, this is syntax. And if you have a matrix A, then immediately you can get L and U. Okay. And here is the for pivoting, and E is the permutation, that's pivoting, partial pivoting. That's why the E is there, and this output form. So here you can see that suppose your matrix you have a matrix you have, then you can. So now your matrix you already know that this LU equal to this LU, just write down LU, L and U, okay, equal to LU and A matrix. Okay. This is your L matrix and lower triangular matrix, and this is upper triangular matrix. But here is a random matrix. Here was the random matrix, okay, and that can be singular as well.
Will be if exchange third and second row. Probably pivoting.
Yeah, there is some problem, as I told you, for any decompositions, anything can happen. But the matrix I have given you, the random matrix. Okay, if you put some matrix like symmetric matrix or any other matrix, say for example, I am giving here B matrix, say here I am giving here the B matrix, say B equal to, say I am giving, say 1, 2, 3, and say 3, 4, 5, 6, 7, 8. Say, let's see what is happening. Now you just give this LU, this is B matrix. What you are getting? There is some problem. It is giving same thing as the earlier. Yes?
Exchange of rows will solve.
Huh?
Rows, exchange rows in L and will be triangular.
Yes, if you do interchange, then only it will happen.
Permutation.
Permutation between lower triangular and but it is somehow it is a singular matrix exchange, that singular matrix. So for example, you take Hilbert matrix, say Hilbert, say 3 by 3. This is Hilbert matrix. Okay. Yes. And now you give this LU, L and U. This is equal to LU. This is Hilbert 3. Okay. Then you put this,
Cube of 3, not cube.
that matrix I am giving answer.
H, R, L, B. B was.
But here is some problem. Already things are there, it is not taking. So you make this here, see. Clear all. There is something inside, so it is taking again and again. Okay, just you take some example here. Here I am taking this matrix. Say A equal to 10. Okay, you just take a simpler matrix, say 1, 2, or say 3, 4. Okay, you just take 2 by 2 matrix. Let's see what is happening. Okay, and this L and U, L, U is equal to LU, and this matrix is yes. The L is upper triangular and the U is also upper triangular, it is giving. There is something in MATLAB, something problem, I think, see the resource of this. Because, yeah, something surprise. See? Okay, anyway. Okay, once again you just see the help LU. If anything, you can check from here. You have already given the LU equal to LU and this one. Well, A is the non-singular matrix you have given us. L is the lower triangular matrix and U is upper triangular matrix. Yeah.
L comma U comma B. So that will give you better version. Permutations.
Okay, let's see. L comma U comma P equal to LU and say this is this. Let's see. Yes. So here what they are doing, they are not doing directly, they are using the partial biotech. Okay. So the permutation is working here. So P you have to give, but sometimes it won't require, because in general, if the numbers are very, say for example, our A matrix was, okay. What happened here, say I am giving 4, this is bigger element in the pivot, okay. This is 3, or this is 3, 4, say. Say this is 2, and then you take this one. Again, you take just LU. Yes. So what is happening? If our pivot element, if you are taking a highest one, so no need to give the partial biotech. So here it is taking, if it is not the biggest element, bigger element in the column, okay, it is taking 12. So then it will calculate the LU decomposition. So likewise for any matrix, one can calculate like this equal to, say I am giving here the RA and B. Now we can try this, say C by 3 matrix. Say this is a B matrix, B or D matrix you take. This is and you put LU. This LU equal to LUP. Here also you can give LU and P. LU, and this is D matrix. D matrix. Okay. Now you set this. P is 1, 1. Yes, it is showing the result that this is the lower triangular and this is the upper triangular matrix. And the P is the permutation matrix, you have that row and the column getting interchanged whenever it is required. And so automatically the MATLAB can understand from first, second, third step, okay, what will be the permutation matrix. Okay, so accordingly it takes column bias. Also you have seen the both the full pivoting also you have seen, okay. So now if you want to write this programming, say for example, you want to write in the M file, okay? You can also write the LU decomposition by using the forward and the backward substitution. Yes? Is not it? So for that, what you do? You have to open your M file. Where is your M file? Here is M file is there. Where is M file here? How to create this?
To change active directory. Here is users HP documents.
No, here it is not showing anything. Open. The M file, how can I open from here? Where it is? Oh, okay. Okay, yes. No. Okay. Maybe this one. Okay. So here you can type this. Say for example, I can write here, if you want to find the solution of this, you can write this function. Okay. And this is, say you want to find the solution x equal to solve. Say I'm giving some file name like L, okay, and A comma B. This is my A comma B. Okay. So I'm writing a M file. So this will solve this. This solve the x equal to b using LU decomposition. Okay, and then LU equal to this LU L comma U comma you can give or you can give the space. This is equal to LU and in bracket. Okay, this will be and you supply this. Now you just give the n equal to length LEN GTH, length of this vector which I am writing here. Okay. And now you put this G equal to the zeros of n comma 1. Okay. This is the zero vector. Okay. Now for I equal to 1 to n, okay, for I equal to 1 colon n, okay, I equal to 1 colon n, you can write Gi equal to Gi equal to Gi equal to, you can write Bi minus this L of I, that means ith row, comma, 1 colon I minus 1. You just recall the class. This is the forward substitution and star G 1 colon, okay, I minus 1. I minus 1. This is what you have got this in your lectures, okay. Zi equal to Bi minus Li1 I minus 1. Okay, this is ith row and 1 to I minus 1 previous, and this star equal to this one. Now you can make this end loop you are loading. Then again you have to do, once you got this G, then you have to calculate the what ux equal to this. So similarly you can put this x equal to zeros again comma 1. This means, okay, and for I, that means this is a backward substitution for I equal to n to how much you will get 1, and here you have to give minus 1 because you have to give the increment, like n minus 1, n minus 2, n minus 3, it will go up to 1, okay. And then what you have, this xi, this is xi, same thing you are writing like value, that gi, okay, minus u I plus 1, okay, colon n. That means it is going from I plus 1 to n, okay, and the star, this should be x, and this is I plus 1 to n. This is what we have done, forward and the backward substitution, okay. And the first one would be LII, okay. This is you close the bracket, and here you have this, and this one is UII, okay. And here also it is LII. Yes, sir. We have missed this one. This is forward and the backward substitution divided by L I comma I. Yes or no? Okay, you got this. Now I'll make this. This should be and another L will be coming this because this is the formula. So this is what you have done this, the forward and the backward substitution. So you can get this. Everything is okay, fine. The function x equal to solve LU, this is the function name, okay, and the LU, and I think here also P would be given. Let's see, we will check this whether we will give this or not, okay, or whether LAUP. So now you set this. Say I am saving solve LU. Where I am solve? Can I put in the desktop? Yes, I am putting in the desktop. Okay. So let's save this. So now your M file is ready. This is your M file and it is saved. And you can save to your any folder. So later on you can use. So earlier in the window command prompt, whatever you are writing, it won't be saved. Once you close, it will vanish. Okay. Once you make the M file and always you make your file dot m. This dot m. Okay, whatever your name also you can put. Say for example, x equal to solve, instead of solve, you can put your own name and you just put dot n with extension dot n. The file is set. Okay. The x equal to solve because it is solving, the x equal to b, lu equal to lu, n equal to length of b because length of this vector b, and g equal to 0 n comma 1, and I equal to 1 to g. This we got this one. Now how we will implement this? Now you come to this here. Say for example, I want to put this a equal to my how I can run this program. This I'll give it 2 comma and minus, either you give comma or give you space, that doesn't matter. Okay, say sometimes you put 2 comma 1 comma this, or 2 space 1 you can also give. Okay, so 2 comma minus 1, and here is 1. I this is 339, 339 and 335, 335. Okay, so you have this matrix. Okay, 2 minus 1 1, and this 339 335. Okay, now I give b. I give the b part is this is column vector 2. Okay, 2 semicolon, yes, this one, and minus 1 and 4. Okay, this I have put this. Now I have to see x equal to whatever function name was there. This is solve, SOL. Okay, this is solve, LU, and this you can put a comma. Okay, a comma. If everything is fine, then result you will get. Otherwise, some syntax will come. Okay, if syntax will come, then again we go back to our programming and we'll check where is the problem. Then we'll run it. So this is the way you have to make this hidden track in many ways. Okay. So now you see. So that is error. Okay, why is error? Recognize the function. Unrecognized the function or variable solved LU. Okay, so anyway we can if we can change the name, okay, it should work. But that is it. Okay, maybe you can give some.
You should change active directory.
Huh?
Active directory.
Because
Directory is C users,
yes,
HP documents.
we have to put this because it is not in the desktop.
Function is in desktop.
Okay, so we have to change.
Better was to accept recommendation.
Where it is, C.
Yeah.
Okay, here it is.
Save again in the same directory.
I'll save this programming again in the document. I can save it. Okay, save as in the document. Okay, .m. Now you see. Okay. Okay,
Now.
now it may work. Yes, it is working now.
If the
Because it was the problem, is that where your file is there, you have to directly, you have to set. Say for example, your file is in the desktop or in document, so your directory should be in the document. So otherwise it will give you problem, because it cannot find where it cannot locate where is your file is, okay? So anyway, we got this with this answer, that something we got x equal to 0, 0, and it is running that file. Yes, x equal to solve this one. So again, you can change your file matrix, A, different matrix, and again you can try this. Say for example, A, we are giving this 1, 2, 3, 4. Okay. And say B equal to, I am giving 2, 3. Now I'll check this whether it is working or not. Like this. There is something error is coming infinity or something like that. Solve the 2, 3, 4. There is something wrong in okay. Say you can change here L comma you read this. Okay. And then you save it. Okay. And then what is your how can you run this file this? Anyway, if you put again this matrix, then you just take this. Yeah, some answer is coming here. Okay. So likewise, you
It
can
was
use
division by 0
yes.
because if
X equal to 0, 0 coming, but yeah, sometimes 0, okay, this is the answer, -4 is 0, 0, 3.5. Because the 0 is coming because we have put x equal to 0, the n comma 1, because it is a vector, first it is taking 0, 0, and then it is putting this solution, exact solution is there. So if I can put there here, it won't come. If I put the semicolon, it won't come again, okay? So now you just see this. So now your 0, 0 is not coming. Why? I have suppressed. Okay, so this is the answer, -4 and 3.5. Clear? So likewise, you can create a M file in your MATLAB, and you can save with a function. Okay, and you solve Ax equal to B. Say we have shown this Ax equal to B. This is LG, x equal to B, and this is LG equal to B, and Ux equal to B. Okay, this one and this. And this is coming forward substitution, forward, and this is backward. Okay. Isn't it? So this one we have found, this first one you just see, this is the one we got GI equal to, your GI equal to this one. Your GI is this one. Okay. And after getting this G, and you just put Ux equal to G, and you got this X. Yes or no? So by using any decomposition, you can solve. So this is the this is your M file. Even if you are taking 10 by 10 matrix, you will get the answer. Okay, you no need to, only you just start the matrix. You just start the matrix and you just recall that function. Okay, solve underscore LU and this A comma B. Because just we put A, B and get the answer. Okay. Say for example, here we are trying about, say you give A equal to, just put A equal to random RAND, say 3 by 3 you can put this 3. Okay. And another matrix B, you just put random. This is side column, and this is okay. This you can give 1 to 3. Okay. What do you get this? Okay. So random RAND, you want to find this 1 to 3. Yes. Entire column. Okay. Yeah. 1 to 3. Yes. It will not come. So anyway, you just to put this matrix B equal to 1, this column 3, 4. You just give this. Okay. Now you take this, solve you use, and then you make it. So you would be getting some insights. So similarly, if I can put say 100 by 100 matrix or 10 by 10 matrix, say I'm putting A equal to RAND. Say I'm giving here 5 by 5. This is matrix you got this. And again you just put this equal to, say I'm putting here 1, column 3, 4, 5, 6. Okay. And then you have this one, and then you get the solve command, this. Okay. And this. So you got them. So likewise, the one you have delivery combination, similarly you can write for traditional combination. Same programming, just you have to change the role of L and U to RRT, that is upper triangular matrix. Okay. So now I want to discuss something. So you can write for full pivoting as well. Okay. And say, for example, if you want to solve with the equation, say, if you have the Hilbert matrix you have, and then you need to know the condition number and their residual, if you want to find this. So for that, what you do, you can write in the window, command window, or you can create one M file for that. Say, for example, if you have this another M file, you can make here. This is my another M file, okay, and I want to write this for n equal to say I'm writing this 4, 4, 8, 12, and this is 16. Okay, this is what we have said, and for n equal to h equal to, I write h equal to Hilbert matrix, Hilbert and n. Okay, this Hilbert in I. Then what I G equal to say say I write once say n comma say n comma 1. Okay. Now B equal to, you want to multiply, say B equal to h, this is B. Okay, and then you write this, say kappa equal to KAPPA equal to con, COND con, and you give H. Con means condition number. Okay. And the error I'll see, the error you just write the error equal to, error basically we are writing in the form of not x minus b. Okay. And the residual equal to, now we check this residual, this is equal to norm of b minus hx. Okay. Okay. This is what you have this. Now you save this with for n equal to 4, 8, 12, 60, h equal to Hilbert n, and g equal to 1 c n comma 1. That means it will create the zero vector. And this is Bexler, means you can solve this by using any decomposition. Kappa equal to condition of h, and the error you have this one. Now you save this one. Save h. So what you want to give them? Say for example, GIAN 1. Okay. And where I want to keep, this is in the document. So let it be.
So it's x equal to h vector.
Okay, x equal to, yes. This is x equal to this one. Okay. And you said this.
And for 4,
What?
and for 4.
N equal to 4, 8, 12, 16.
Semicolon.
Yes, you can give this semicolon here. Here also you can give semicolon. Okay, here also you can keep. Okay, that means it won't show here. Now you have this shape.
And in the end,
Okay, here and also you have to write this and this, because if 1 for 1 end, 2 for, you will give me 2 ends. Okay.
not,
So now this saved with
not,
the,
I think not semicolon in first row.
this is you don't do one. Okay. Okay. This is saved here. Now you run this program. So you will this is your file. With this. Okay. Now you just to see what is the error. Because the x you got this. What is your x? Just type this. And you see the error. And what about kappa?
Run is right.
Eh?
Right is run. Right,
This one?
green.
Okay.
And run.
This one. Star. So whether taking H or not. Will H. There is some problem.
Command line and run is right.
This one, H here is getting syntax. H is semicolon, okay? Semicolon.
It is not evaluated.
Okay. Okay. This What is H? Mhm. That-
To evaluate this,
Which,
to evaluate first row.
this first row?
No, above command line of MATLAB around this. It should be evaluated.
Sir. Sir, B is B, the vector B at
Okay.
Ready, you are defined.
Yes, yes, yes. That is something.
B.
That's
Equal to one, that should be B equal to one small n, one and all.
now here is a B we have defined or not? No. Here B equal to, we have B equal to H dot B. Okay, let's see. What is this? There is some error in that. N84 Gilbert N once N1 B H dot G X and the error is kappa condition of H, error norm of X minus B, residual is this. So sometimes it okay, we'll see this one in our next. So okay, we will do for the next thing. Maybe yes. Can you come here? Here is the run repair. Okay.
Evaluate and then.
Yes. But there is a run over there.
No.
So now it is coming here. Okay, that's right. You see, there is a run command is there. Here is the run is there. So we have to keep this run.
Now,
Run your file. Okay, here you have to give it. Run your file. So then you will be getting this PLC clear all. Okay, now you run this. So n equal to 16, your condition number is this. Okay, condition number is this much. And how much error you have? 8.8 and the residual is this one. The error is it's too much. Okay, this is 8.8. So this is for Hilbert matrix. And when n equal to 16. And if n equal to, say, n equal to 8, so what will get this one? So we'll get this.
it will be better to put fprintf command inside
Ah,
for
okay.
cycle. Then we will obtain for each n.
N equal to?
Repeat this command in for cycle.
Okay, okay.
Complete copy.
Acha.
Cut and put in.
I can copy this,
Cut better.
copy.
Cut. And then pass inside as last command.
Okay. Yeah.
Enter.
Yes.
And then we will obtain.
Okay. Yes. Yes.
We will obtain it in each step
Okay.
and
Yes.
get trace. Run again.
Yeah.
Here is.
So here it is CU. For n equal to 16, and you see the condition
It was
number
previous exit. Now we have for all values.
for all values. Yes.
No guide value we have.
N equal to
First from 4.
n equal to 14, 16, 4, 8, 4, 8, 12 and 16. Okay. This is n equal to 4. Okay. This is your number, condition number, and the error is this, and the residual is this. The residual is very less, but the error is very big one. For the n equal to 12, n equal to 4, it is fine, error. But as you go and increase your size of the matrix, say n equal to 16, and the error is coming 8.8. Got my? So if I put this, say m for here I'll put instead of 16, if I put say 32, say 40, then you check this, what will happen this, then this. Now you see how much error you are getting. As you go and increasing,
It goes from.
and your condition number is increasing, okay? So here you can see n equal to 40, this is your residual, and this is your error. Okay? Got my one? Error equal to x minus z, because and the residual is norm b minus hx. So this is the way you can calculate the condition number of the Hilbert matrix. Okay. So other way, you just to put here the condition number also, you can get directly. Say for example, COND. You can just put Hilbert, which will be 4, say 4, and I'm giving here this. This is your condition number. Similarly, you can put for the other matrix, other size matrix, say if I'm putting 40, also I will get this one. Okay. So you can also see for other norms, this is you just give FRO, FRO. This is for the Frobenius norm. Okay. And you get this. And similarly for the one norm, if you want to quickly, you want to calculate, you just put INF, infinity norm INF with the inverted comma. So you get this immediately, you can check this condition. So all such things you can, for one norm also you can check, you just put one. Okay. And if you are not putting anything, that means it is understood, it is taking for two norms. And if you want to put any two also, same will it will be. That my point. Yes. So this is the way you can write your programming, MATLAB programming. Now similarly, you can write the any decomposition for the Hilbert matrix. So same way that we did, just you put the Hilbert matrix. Okay. So if you get the Hilbert matrix, then you can see the how much error you will be getting. So here you can check this solve here, this solve with this. Here you can put if I run this one. Some error is coming here. Not enough input. Okay, you just delete this.
Is A defined
Oh, okay, yeah.
and B
Now we'll define it.
make.
So here will define, yes, exactly.
All and
It is asking because we have not defined
define
it.
again.
Say for example, I am giving here A equal to Hilbert. Say it is 5 or 5 you can give. Okay. And just B equal to say vector you can give 1, 1, 2, 3, say 4, 5. Okay, 1, 2, 3, 4, 5. Now you see this. What is your x? X you see. This is x. And what is your n? You just type here. Okay, because L you are not getting here from here, because L already, this is the solution you are getting X, okay? This is the solution you get. So for any matrix, you can check and you find the residual also, the LU, and you just find the norm of, because already the LU is there here, and GI and the LI, because L is not taken. And you, what is the problem? But giving answer and L and U, it is not finding. Explain error. Let's see what explaining. Unrecognized the function or variable L. Or in other way, you just put this Hilbert, you put this LU, L comma U. This is equal to LU of this is Hilbert, HILB, and you just give this is 5, and you'll get this LUP you can give, okay, or you can give P also, and you see what you are getting. This is your P matrix, okay, and this is L and U. And L and U you got. Now you just take the norm of this, because if this A equal to NU, Hilbert matrix A equal to NU, that means A minus NU should be approximately equal to 0, yes or no? And now you check from here, you check how much error is coming. This I can write norm of L minus U, and LU, A minus L star U. Okay? So I am getting huge error. This is 0.2. This is huge. So this is for the Hilbert matrix. And if you check for other matrix, if you increase your size of the matrix, and this error will increase. But we should get this approximately equal to 0. In that case, we are getting a big number. So because Hilbert matrix is ill condition. Correct?
We need return common for LUP, because LUP are used in function, inside function and forgotten. Outside not available, X is available.
Yes.
Because we had X equals solve, and only X is exported.
Yeah.
We should use a return function and then LUP
Yeah,
can be returned.
so for here it won't work.
Otherwise, LUP are only inside function.
Yeah, okay. We
As a
don't
parameters.
require, but if you want, then you can just take the X and the error you can know. Okay. Okay. So in your tutorial, you must have seen that how to get this. Suppose if you have I have discussed something, say, if a matrix is symmetric, okay, symmetric matrix if you have, then you know the eigen decomposition, is not it? It is diagonalizing. Okay, if A is symmetric, then D comma V, this is the command EIG of A. Okay. If A is symmetric, if A equal to AT, that means A is diagonalizing. And diagonalizing. Yes or no? And how you are getting this? You remember And also you can take A is a Hermitian matrix also, A equal to A star, where A star equal to A conjugate and it's a transpose. Okay. And remember, if A is a complex matrix, Cn cross N, then you have A equal T equal to U A U star. Yes or no? Because this is called source decomposition. Remember, source decomposition. So if I apply to this to Hermitian matrix, A equal to A star is Hermitian matrix, and we'll see whether this matrix is diagonalizable or not. Okay. Yes. So what do you do? Here is U T, say U T U star, is not it? And U T U star whole star. Yes. And U T U star, this is U T U star. And if you do multiply left hand side U star of both sides, then you will get T U star equal to what you will get. Yes, here is wrong. Here is something. This should be U star. Sorry, U T star. Okay, and T star would be there. Okay, and T star, U star. Again, you multiply U both sides, you will get T equal to T star. Okay, and from here you can say that T is a diagonal matrix. If it is a diagonal, then only it would diagonal. Yes. Yes, sir. So if the matrix is symmetric, then you can get it is diagonalizable. That means A is similar to some non-similar matrix, yes, D S inverse. This is. And what would be the MATLAB command to check this? Let's say, for example, A equal to AT is there. It is symmetric, and just you type VD equal to eigenvalue of A. And here you will get V, this matrix you will get, and where columns are the eigenvalues, okay, and the D is the diagonal matrix, with diagonal entries are eigenvalues. Okay. Now we'll see in the MATLAB whether for the symmetric matrix diagonalizable is coming or not. Yes or no? Right? So say for example here I am taking A is a matrix. Say A in the matrix here I am taking say 1 3, and this is say 3 4. Okay. Or this you take 1 3 plus I, and this you take 3 minus I. Yes. This is Hermitian matrix. Yes. If this is a Hermitian matrix, Hermitian, why it is Hermitian? Because A equal to A star. Now we just write down this B comma D, B comma D. This is equal to EIG of this A, and you just check this. Now you see the D is minus 1 6. These are the eigenvalue, and B is these are the eigenvectors. Okay, these are the eigenvectors. So how you will find these eigenvalues, eigenvectors? Because EIG of A, this is equal to this one, minus 1 6. This is a command. If you are putting any matrix A, and if you put this I of A, that will give you the eigenvector of this. And this the eigenvector, the first this V, if I extract first column, first column, this is the eigenvector corresponding to eigenvalue minus. Okay, this is the eigenvalue. What is it? This is the first column of this matrix. This is the first column. The first column would be the eigenvector corresponding to the eigenvalue -1, and the second column, this would be the eigenvector corresponding to eigenvalue 6. So that means your matrix A is diagonalizable if A is Hermitian. Similarly, you can check if your say matrix is Q Hermitian, all the eigenvalues are purely imaginary. Okay. Hermitian, all the eigenvalues are purely imaginary. Similarly, you can check for the normal matrix, if it is there, then matrix is diagonalized. Likewise, you can just use the source decomposition, you check this T equal to something, T star equal to T star T. So basically, if you apply this, yeah, if you have a normal matrix, say A star equal to this equal to A star A. Yes or no? If A is normal. And also you know that this T equal to U star AU or A equal to U T U star. And if you do substitute here, you will get T star equal to T star T. Okay. And this is possible only when T is diagonal matrix. T is a diagonal matrix. Okay. This is because T is a diagonal matrix, and this normal under that is a result in the linear algebra. If a matrix is normal and triangular, then it is diagonal. Okay, this is one way, basic result of linear algebra. So you can check from here in MATLAB also, you can check, you put a matrix here and which is normal. Can you tell any matrix which is normal? Can you tell this? This is obvious. Any matrix which is normal. So you can check this. Yeah. Okay. So similarly, you can write about the code for the least square solution as well. Okay. The least square solution, if you have this overdetermined or underdetermined system, and you can just write the least square solution for this data fitting of the core. And also you can check here. And as I told you about this condition number, and here it is mentioned for P equal to norm type 1, flow and infinity. So the one I told you, this P can be replaced by 1 sometimes, and this is FRO, this is for the Frobenius norm, and this is for infinity norm. Okay. Now, how you get this Schutz decomposition from your this one? Say, for example, you are putting this. If you want to know more, then you just put SC, SCHUR. You will get this Schutz form of matrix. So T equal to Schutz of A, that means this is a command U comma T and Schutz. Okay, this is what, and you just put the matrix here. Now we check this. Suppose you have a matrix whether we are getting this any complex matrix, you just take CLC. Always you put CLC and the clear on, so that anything if it is saved, then it would be erased. Okay. Now say I am giving any complex matrix here. Okay. So this is 1, say 3 plus 2i, okay, and this 4, 5 plus 7i. Okay, this is my matrix. Okay. Now we'll check this, whether we will get the triangular matrix or not. Okay. So you just put this command, this say U comma T, okay, and this is equal to 2, this is your A matrix. Yes. You just see this, T is a triangular matrix. This T is a triangular matrix. Okay. T is a triangular matrix. Now we'll verify that U star, U dash star, TU star A, sorry, U minus A, and you take the norm. This is and you just put this, maybe some other way you take this, you start, this is this. Yes. This is what we got, this is around it is 0, this difference is 0, that means A is nothing but EQ matrix. Okay. This is Schutz decomposition. I told any matrix you can take, a complex matrix, and the Schutz will give this U, T, Q this, and the T is a triangular matrix. And you can check U is a unitary matrix, as I told you. U this star U, you see this is an identity matrix. Okay, U star U equal to identity matrix. As I told you, that any complex matrix can be transferred into triangular. Unitary triangular. That means A equal to U star T U. Clear? So any complex matrix you have seen that, or you just check norm of U is equal to, it would be 1. Norm of U equal to 1. This is, that means this is, okay. And if you want to write a M file, you just create a M file here, M file for the Schutz decomposition. You can type this, that A equal to, you just type this A equal to RAND. You take any matrix, random of A, okay. You have this, say I am taking here 4. You just take the 4 matrix, what I call. Now you just take this, this is, you just Q, U comma T, U comma T. This is equal to STHUR and this is it. Okay. Now you just take this norm of this A minus U star T U. Okay. Clear? Then you just run this, calculate this difference. Okay. Calculate this difference. Okay. You just set this with the GIAN tool. Always you have to put with the M file. Dot M should be the extension, and this is in the document, so I am writing here set. So your file is set. Okay. So whenever after 10 years, if you want to extract email, this is set somewhere in your directory in document, or you can put in your email box. Okay. Whenever you require, just you extract it and you run it. Now you see, for the 4x4 random matrix, and this is the difference norm A minus UT, U star T, U dash. This norm is 0. That means around about 0, 10 to the power minus 15. This approximately equal to 0. So you got this A equal to always UT, U star or dash. In MATLAB, dash means U star. This means this is nothing but it is taking complex conjugates. Okay. Yes. Automatically it takes. You just check this. I am giving here a matrix is this A equal F equal to this 3 plus 3, say 4 plus 5i, and this is 10, this is 9 minus r. Okay. This is matrix. If I put F, this is complex conjugate. Yes or no? Yeah. This is complex conjugate. This is star means this is test. Okay. Transpose nahi, complex conjugate. Transpose. Okay. It is taking conjugated. Okay. So likewise, you can verify that source decompositions whether this is valid or not. Okay. Now similarly, you can also talk about the Cholesky. Okay. Cholesky factorization. How you write the Cholesky factorization? Suppose A is the matrix is there. So I can write here say A equal to say CLC, you just put clear all. Always you have to put like this. Otherwise the previous matrix it will be recalled. Okay. Yeah, always you make it fresh, clear all. And CLC means everything it will erase. Okay. So I am taking here A is a matrix here, and it is symmetric. You just take the symmetric positive definite matrix, or you just A equal to, you just take this 1, 2, and 2, 3. Okay. 2, 3 you take. And I am putting here R equal to Cholesky CHOL, and you put this A matrix. Matrix must be positive definite. Okay. So if matrix is positive definite only, the Cholesky factorization is important. Okay. So here you just put the help here you see all this about the Cholesky factorization, R equal to Cholesky, and the syntax. This MATLAB function factorizes symmetric positive definite matrix A into an upper triangular R that satisfies A equal to R star, R dash star R.
Instead of A, it will be good to use AA transpose.
Okay, yes, good idea.
B will be symmetric.
Yeah. So what you do is,
Still that.
yes, okay, fine. You just take this A equal to, whatever you have kept this 2, this 3 and 4. And here taking C equal to A transpose A. Okay,
Star.
star, okay. This is star. So I got this is a positive definite. Okay, now I can put this.
What are eigenvalues of C?
We just see the eigenvalue. If all these eigenvalues are positive, then we can get sure that
Of C,
no,
of A,
this is not positive definite.
of C, not of A.
Of C,
C.
okay, sorry. I put C.
We prepared C to be positive.
C. Yes, C is positive definite matrix. C is the only. Now we can apply this solution. It will work. So R equal to this R equal to CHOL and this is C. So got it. So generally putting this positive definite matrix, it would be difficult. Any matrix, real matrix, you just take A star A, just you get a positive definite matrix and just you put
AA transpose.
put Cholesky factorization of that. Okay. And also you can write the M file like we have done for the LU and the source decomposition. You just create the M file, you write matrix everything, and you share it like that. So now you can check this matrix. There are special matrices and Wilkinson matrix. This is also matrix which is called Wilkinson matrix. If I put this Wilkinson, W equal to Wilkinson N, this eigenvalue test matrix, this MATLAB function is this Wilkinson. This is another matrix which is very ill-conditioned matrix. Okay. Say I am putting 4. Okay.
Small.
Small. Yeah. This matrix is diagonal matrix, and this is very, very inconditional matrix like Hilbert matrix. Okay. Clear. Now you see the LU decomposition, whatever we have solved this here. Here you can put this with A equal to Hilbert matrix. Say A equal to say Wilkinson. Wilkinson. This is 4. Okay. Wilkinson 4. This is matrix you have. And now you solve this. This x equal to. First we have to run this. Yes. Now you put x. Okay. You put A equal to this one, and you find the x.
Need to start program again. We need again a run of this function.
No, I have already run. I have run this. say, B we have to put. B equal to, this is 4 by 4. So 1, say 2, 3, 4. This is we have given. Now FC you can get.
Run. Then
Okay. No, I have already run. I have already run this. Line 2. Line 2 is showing. So it doesn't need require this P or what? Okay, let's check.
is I defined.
Huh?
I is defined. A is defined.
Yes, yeah, I am defining here.
B defined.
This A is defined, this one. A is this, and my B is this one. This is B. Now you see X. So there is a directory problem. Sometimes it is taking out, sometimes it is not. Means unrecognized function X. X equal to this. Anyway, I can. Okay, we'll make this. Again, we'll do this. Run this. Now you define this matrix. Now define this B and see the X. That is something.
Run again.
No, I have run. Okay. Let's check once again. But sometimes it is giving the right answer. Why it is showing this? Okay. So if you
X
put,
equal to solvent.
huh?
You write X equal to solvent.
No, already X is done the solving. If you put this also, it will give error, I think. It is taking. But if you take any other matrix, say A equal to, say you are taking random, say 4 random 4 matrix, and you put this B equal to same thing, 1, 2, 3, 4. Okay. And this is matrix you got. Now you put X. Now it is not taking. Earlier it was working, but now it is not working. There may be something problem in MATLAB. May sometimes it happens. Okay, let's see. So now you take this. You just you can just check this and we'll see later part of this. And similarly, you can try for that. Now you see, if you calculate the eigenvalues of this Wilkinson matrix, okay. B comma D.
Where is part function x equal?
Huh?
Where is part function x equal? So earlier. First row, function, no function.
Oh, I,
Not with cat.
no, it is there.
After function,
This was already there, but it was giving error. Okay. Now you see the other things of this Wilkinson, whether Wilkinson is symmetric or not. Wilkinson, some characteristics of Wilkinson matrix. You can check this Wilkinson. This is also very ill-conditioned matrix. You just put this count of condition number of this matrix. So as you go and increase this size, it will increase. You just see if I am putting 10. So similar to Hilbert matrix, you see this is 7.48974, the Wilkinson matrix of size 5. And if you take the 10 and the condition number is 24. So as you go and increase the matrix size like Hilbert matrix, the Wilkinson matrix is also very sensitive matrix. Okay, the sensitive matrix. So for that you can see it's the characteristics of eigenvalue. Their eigenvalues are very close to each other. Eigenvalue of this Wilkinson, say this is 10. You can put this Wilkinson 10 and this. These are the eigenvalues, and you can see that their eigenvalues are very, very close to each other. This 1.08, and you take this eigenvalue, say I am taking 20, and you can see that the eigenvalues are very close to each other. Okay, you can see this, how they are close. 3.48, 3.51, 4.49, 4.50, 5.50, 5.5003. They are very close to each other. If they are very close to each other, that means this is sometimes it is called defect. This is defective matrix. Say they are very close to. It is simple, but it won't give you the good results. All the eigenvalues are distinct. You see that the eigenvalues are distinct. Okay, there is no repetition. Is there any repetition? Where it is? Yes, 8.7107. 10 point, but what about for the small matrix? 4, is there any repetition? Here you see, repetition is there? No. Eigenvalue of I of 4. Is there any repetition? No. No repetition. You make this 6. There is no repetition. So as we go and increase the size of the matrix, and you will see the eigenvalues will be very close to each other. If they are very close to each other, that means that matrix is called ill-conditioned. So whatever characteristic you have seen in the Hilbert matrix, this is called Wilkinson matrix also. There is plenty of such matrices. You can see GIAN matrix. This is another matrix you see. This is another ill-conditioned matrix is there. GIAN, not found. Okay, this is not available here because already. Okay, then put this capital GIAN. No. You just put Hadamard matrix, say Hendermont matrix, okay? Help. Cauchy matrix. Okay. Help. Cauchy. Okay, this is also or help. There is other matrices like Gallery and Hilbert. Yeah. So from MATLAB you can find lot of ill conditioned matrices, where like Cauchy matrix and Chebyshev, and this is Topli's matrix also you can find, and you can verify its eigenvalues and eigenvectors and its characteristic on or the sensitivity of the LED composition for this ill conditioned matrices. Okay. So any doubts? That part we have to check this, how this LED is not coming. Sometimes it is coming and sometimes it is not coming. Either it will be a problem of in the software, if not fully installed, sometimes it will be making a problem. But if any doubts? Anyway, if no doubts, we can stop here. Okay, thank you.
You didn't use my computer, you told me to use, and I put my computer here, okay. You had better MATLAB,
Better.
newer MATLAB. My MATLAB is 10 years older. Because of that, I put my computer here.
I stopped on it.
Okay. नहीं यहाँ पे कुछ प्रॉब्लम हो रहा है वो MATLAB fully installed नहीं है because some cases it is showing the result and some cases it is not.
Line 18 should be verified in your function.
No, unless
In
it
one
was
moment, I
some result.
observed the line 18. But it's true, once more.
No, it was
Next time we find A and B.